All right, so if you git cloned the repo here, so again, you open File, New Terminal. This opens up this System Terminal window, and you can git clone. And the git clone command is also in the instructions, so just make a copy paste so you don't forget or mistype anything in this command. If this is erroring out, you probably have just a typo in there, so double check. All right, and when you clone down everything, this will pull down our workshop code, and you can, on the left here in the file browser, click in here. And then what we're doing today is running this quick start. So click into the quick start. And I'm just going to minimize my windows here that I don't need anymore. So how the workshop works is we're going to walk you all through those notebooks that you find in here. So from 00 through 12. And let's just start sequentially here. So the first one is the overview notebook. And this is really for all of you who might not be familiar with Jupyter environments yet. So this is kind of a playground. You can just try to familiarize yourself. And again, here's a link to the book. More important also, some of you mentioned you see this no kernel at the top. So the kernel is basically the compute and memory resources that is powering this notebook and the code we're going to execute. So if you see a no kernel, you can click in here, and then you can select the Python 3 data science kernel and just say, yep. And once that is starting up, you can see here at the top that it's now showing you the vCPU and the gigabit here. So the CPU and memory resources. And that means we can execute code now in this notebook. So always make sure you have a kernel assigned in case you don't see anything happening. All right, quick intro. We always have people that are new to AWS. So quick overview here of the AI and ML stack. So the portfolio of services that AWS offers. And in the meantime, there's really a broad set of services available and capabilities in the services. And AWS tends to organize all of the services in those 3 layers. So the top layer here, as you can see on this visual, is the AI services. And those are services that already come pre-built. For example, if you need a translation service, if you need an image recognition, object detection, transcription service, etc., NLP service, those are the services that are available, and you can use simply with an API call and embed in your applications, right? So there's normally not much need to develop a translation service, language translation from scratch. Unless you have very specific text data, for example, you need to train models on. But if it's general language translation or other tasks, there's a good amount of services that already can do the work. And you can also customize those services often to specific data. For example, the Amazon Comprehend service is an NLP service, and you can train the built-in model with your custom data to make it even more accurate for your specific case. We're going to work today on another layer here, which is the ML service layer, and primarily Amazon SageMaker. So SageMaker is the managed service that you can use to really build custom models, building, training, and deploying the models. And for those of you who might have worked with SageMaker before, we really added a lot of new capabilities over the last year, specifically at last reInvent, which is the large conference of AWS every year. So we have a lot of goodness, and we're going to show you all of the new features in here that got launched. So for example, we will step through the process of building an NLP model. So we're going to use a BERT model specifically. And we're going to introduce you to all the specifics of the model here as well throughout the workshop. But just as an overview, we will use a pre-trained BERT model. So that makes it even easier, and then customize it and fine-tune it to our text data in this workshop. And we will show you features such as the feature store. So when you prepare the data and do feature engineering, you can also store and share features. We're going to introduce you to this concept and show you how to do it. And we will then walk you through the additional new functionalities One of them is detecting statistical bias in data. So we also have that part coming up. And then we're doing the feature engineering for the BERT model, fine-tuning the model, and then also creating a pipeline. And the pipeline basically brings together all of the individual model development steps and then helps you to orchestrate that in an ML pipeline. So, and this is all capabilities of SageMaker. And you're also already seeing one additional IDE, which is SageMaker Studio, which is kind of bringing together a lot of functionalities in here. You can visually see the pipelines, for example. You can visualize a lot of the analysis that we're running here. And it's also just an integrated IDE here to perform all of the tasks. And the most obvious one here is also the hosted and managed notebooks that we're using. All right. Let's go down here. If you execute the cell, you can just click in here. So if you see those code blocks, this is the code we're executing. And you can click in here and do a Shift Enter, and this is executing the code. And you can also, for example, not just write Python code, but you can also include HTML code, which is fun. So we just put in here links to our Twitter handles if you want to follow us there for announcement around new workshops, webinars, etc. And also, if you like today's workshop, we also appreciate GitHub stars. So if you like, you can give us a GitHub star as well after today, and we appreciate that. You can also embed just any iframe, which is cool. So here we're just showing how you can just show any website code. Again, this is our website here. And let's go down to the use case. So I already gave you a quick overview. So what we're doing is we do have an NLP use case to work on today. And we're using the popular BERT model. And we're using a pre-trained model. So if you're familiar maybe from computer vision with transfer learning, it's kind of a similar concept where we use a model that has been trained in NLP specifically on large text data. So for example, BERT is trained on Wikipedia and the Google Books corpus. So we could use that model and then just fine tune it to our specific data. And this is what we're going to do. So we do have a product reviews data set that we're going to use. This one here is showing the Amazon customer reviews. And we're going to fine tune the model on those reviews and then develop a text classifier, which will give us a star rating based on the review text we're feeding into the model. So this will be our fine-tuning step. And if we look here at the process, so we will use a pre-trained model. We're using the Hugging Face open source NLP library. It's a pretty popular one that comes with, I think in the meantime, thousands of those pre-trained models that are available. So we're going to pull down one variant of BERT, which is called Still BERT, which is really just a distilled version. So it requires less memory and compute and still has pretty accurate results. And then we generate the features from our text data set. And we're going to use TensorFlow in this workshop and adding this text classification layer on top of this pre-trained model, fine-tune it. And then we're going to have the text classifier that's giving us the star ratings. And to make it more fun, we will also bring this together in a pipeline. So you will learn how to build those SageMaker pipelines that orchestrate the individual steps. And here you can see a screenshot. So we will start the pipeline with the processing step, which will generate the features, then fine tune, and we will evaluate the model. So to check how good is the performance, how good is the accuracy. And then if the accuracy meets our defined condition, so let's say we want to have a model that's, above 90% accuracy, then we would register the model and also create a model here, which is really just giving us another object to deploy the model directly in SageMaker. All right. And the last cell in every notebook will have here the release resources. And this is really just housekeeping. And if you execute this cell, you will notice that the kernel shuts down. And this is exactly what we're doing. So we're just freeing up the memory and CPU resources. Otherwise, we're going to have 12 notebooks running and consuming memory. So whenever we're done with one notebook, this last cell shuts down the kernel and releases those memory and CPU resources. So if you're running through those notebooks, at one point you will see that the kernel flips to no kernel. And this is mostly when you execute the last cell here, which shuts everything down. So this is totally expected and really just helps us to do a little bit of housekeeping. All right, so this was just the overview notebook. Hopefully everyone feels good about using those Jupyter notebooks now. And let's do the next one. So we will open the 01 setup dependencies. And what you can also do, run this notebook, please. And this will take a little bit longer because it's doing all of the pip installs. So what you can do is a kernel, restart kernel and run all cells. And this is really just, giving you a clean kernel start and then executing all of the cells sequentially here. So you don't have to click each and every cell. All right, so I'll show you a little bit what's happening in here. So again, this is just setting up additional SDKs, libraries that you might need to work and develop your models. So first of all, we're checking here on the Python version. So this one has 3.710 installed. And you will see here a couple of pip warnings popping up, so you can ignore them. It seems like some dependencies have changed in the last days. So it's just warnings coming from pip, so you can safely ignore them. It's not affecting our code, everything works. Once in a while, when something changes, those warnings pop up, as you probably know. All right, so what we're doing here, and I'll just show you, we're installing the SageMaker Python SDK with a pip install SageMaker. And this is giving us all of the additional high-level functions to work with SageMaker here from our Python environment. And we're also installing 2 more libraries. So one is here, SageMaker Debug, SMDebug. And we're going to show you this when we're training or fine-tuning our model later on. SageMaker Debugger gives us visibility into the model training process. So you can monitor, for one, the compute instance resources. So how much CPU is consumed, how much memory is consumed, and also gives you warnings in case there's bottlenecks detected. So this is really cool if you want to observe if, for example, you're running on a GPU and whether the resources are utilized or maybe underutilized. And also with CPU-based instances, if you need to provision maybe a bigger instance, or even if you can scale down to a smaller one. So really good insights from the infrastructure resource utilization, but also giving you visibility into the framework metrics. So again, we're using here TensorFlow. So SageMaker Debugger will also monitor the framework specific, how much time is spent in each phase, maybe in the initialization or in the training steps. And you can also capture tensors. So all of the information in the tensors, if you really need to debug on a very fine-grained level. So we will see this in one of the next notebooks. And then I'm also pulling in here SageMaker experiments. And experiments will show you and give you the ability to basically compare and catalog the different model development experiment runs you're doing. So here you can log the individual steps you're performing, the pre-processing, and for example, the different parameters you're setting, and keep track of everything. So basically your experiment lineage tracking. All right. And we do have sometimes in the bigger workshops, PyTorch code as well. So we're pulling in PyTorch here that runs for a little bit. And we're also installing TensorFlow. And then for the pre-trained models, as I said, we're going to use the Hugging Face transformer library. So Hugging Face is this very popular NLP open source libraries that's giving us here pre-trained models in the transformer library and a lot of goodness. So we're also making sure to pip install that library. And again, we're going to show you in the next notebooks how you can work with your data on AWS. So the first steps will be to ingest the data into an S3 bucket and then register, catalog the data. And we're going to use SQL queries. So we show you how you can run SQL queries on the data to explore without the need to actually move the data anywhere. And we're using a service called Athena. And this is a client, a PyAthena client we're installing to interact again with a service from our Python environment here. All right, the larger workshop does have also redshift examples. So we're also installing a SQL client here, SQL Alchemy, which you could use to interact, for example, with redshift as well. And then you can really install anything you might need. So during the workshop, we figured sometimes we need the zip tool, which doesn't come pre-installed. So you could always add additional libraries. You might need utils with either the pip install or conda install commands. So here we're just adding the zip as well. So we can unzip stuff. And for the visualization, we're installing matplotlib and Seaborn. So those should be familiar libraries if you're working with Jupyter and visualizing. So yeah, pretty popular libraries building on the pandas library to visualize data in here. All right, and just checking everything got installed. Again, the notebook will run a little bit, so just let it complete pulling down the SDKs and installing everything. And at the end again, here you will see we do have a %store command. If that is new to you, that is called Jupyter Magic commands. And in specific, the %store, what it does is it lets you store variables in the local key value store right here in this Jupyter instance. So we're creating a couple of variables just to make sure, for example, here that you've run the notebook, so we can check it in another notebook. And this will just be stored in a local key value store, which you can print with the %store command. And you can see here, this variable got stored with its value true in this local environment. And this helps us if you need to reuse variables in the following notebooks, let's say names of trained models, locations where you store the data, etc. So you will see us using this in every notebook here. And then we're also in the next notebook pulling in this variable again and checking if everything is set correctly. All right, and the last cell here again is just releasing the resources. So if I run this, it will shut down the kernel here. All right. So when that is done and the notebook is completely executed, feel free to close it. And maybe just quickly checking in with Chris here, how we're doing, if there's anything you want to maybe address before I move on to ingesting and querying the data.
A couple questions about like what is Parquet, what is Redshift, difference between Redshift and Athena.
Yeah, I'm coming to that.
Okay, so Vikas Ansha is going to explain that.
All right, so yeah, I'm gonna give you a quick overview of what the tools are, and yeah, let us know if you're not familiar with anything we're mentioning. All right, let's just maybe get started with the 02 notebook. So if you open that, and while it's running, I will explain. So what you could do is kernel, restart kernel, and run all cells. And you will see then that here the cells start with the star, the asterisk, and the numbers. All right, so while the notebook is performing its job, let me briefly explain what we're doing. So everything starts with the data, right? So the first step here is to get our data set into an S3 bucket. And this could be maybe you have built a data lake on S3, or you're ingesting training data just into a bucket, which we're going to do here. And then the first step might be to explore, right? Because you need to understand the data better, if it's enough data maybe for your model training, if the data is clean enough, if you need to do some pre-processing. And what we've seen with customers and companies, pretty much 80% of the task is normally spent in those projects on preparing and cleaning the data, right? So it's a big step, because without good data, the model cannot produce good results. So we want to make sure to understand the data. And this is what we're showing here. So we're gonna ingest the data here into an S3 bucket, which is just, standing for maybe a bigger data lake. And to query the data, we're using a service that is called Amazon Athena. Athena is built on the open source Presto, if you know that project. And it's useful if you want to query data that is sitting in S3 without the need to move it, right? If you think about Redshift, so the question Athena versus Redshift. Redshift is the AWS data warehouse service. So in traditional data warehousing, you have very structured data, right? You're creating your databases, your table schema, and then query the data in the data warehouse, and it's optimized for exactly those heavy analytical queries. Data sitting in an S3 bucket, it's normally, a bunch of files, maybe CSV files, maybe tab-separated TSV files, etc. And not necessarily always, in a structured way. So the different files could have, different information, etc. And the beauty of Athena is that you can use that service to run SQL queries on the data sitting in S3 without having the need to move it or transform it. So what we traditionally call the ETL, the extract, transform, and load, which is usually what you need to do if you're ingesting new data into a database or into a data warehouse. So what we're showing you here is, in this 4-hour workshop today, we're not doing the Redshift examples. You can also obviously ingest data into Redshift, but we're showing you how you can use the Athena service built on Presto to run SQL queries interactively on the data in S3. So this is the idea. So, and I'll quickly walk you through here, and then I'm going to explain also the Parquet data. So first of all, here we're importing the libraries we need. So Bodo3 is the general Python SDK for AWS. So this includes all of the services. And then we're also importing the SageMaker specific SDK here. And then we're just setting here a couple of variables. So the current session we're operating in, the default bucket that we can use that SageMaker sets up for us, the IAM role. And IAM gives us the identity and access management role permissions. So everything we do needs to have the permissions. So this role that we set up will define what we're allowed to do in here. And also we're pulling the region information and the current account ID. And this is really just a little bit of boilerplate code you will see in every notebook pretty much. All right, and then specifically, as we want to query the data with Amazon Athena, we're now using the PyAthena SDK here. So we're importing PyAthena and specifically a connect object, and also pulling in pandas to wrangle the data here. All right, so I mentioned briefly that we're working with product reviews data, text data. And here you can see the columns. So the data is available in Parquet format. And next question will be, what is maybe Parquet data? So Apache Parquet is an optimized binary file format to store data based on columns. And this is particularly helpful if you're running analytical queries such as SQL queries. If you think about a SQL query, let's do the very obvious one, select star from, which is always a bad idea, but always the easiest to understand. So you would select the information you're looking for, the columns you're looking for, and you can, for example, do a where clause, right? Where maybe the product category equals books or equals ebooks or equals whatever you select. And this will filter the results by a specific column and a value, right? So think of it, product category as a column and maybe the books as a subset. And if you're storing the data physically in a columnar file format, that speeds up those analytical queries because you can scan exactly the storage location that keeps the data you're querying. And this is really Parquet. So again, Apache Parquet, a binary file format that is super optimized, especially for running analytical queries. In machine learning, you would normally probably work with row-based. So let's say CSV data, as you know from Excel, comma separated, or maybe tab separated data. As machine learning models operate on a row by row basis, right? So moving forward, when we're building up our model workflow, we will use the row-based, either CSV or TSV data. But for analytical queries, which I'm going to show you here, it's always the best choice if you have optimized, and for example, the data in parquet. And there's various ways, if you have one or the other format, to also convert, for example, CSV into parquet or parquet into CSV, etc. So also possible. All right, so we're going to use and set up Athena here. So here again, the schema. We need here just to define basically a query cache location in our S3 bucket. And this is really just where the query results are stored. So we just set this up once. And then you see here that we're actually defining a database name and a table name. And we're using that to create a schema. So the important thing to understand is we're not moving the data out of our S3 bucket. But in order for us to run SQL queries on it, we need to define the schema. And this is what we're doing here. So we're using a database that is in a data catalog service that Athena supports. And AWS also offers the data catalog, which will store the schema information. And in there, we're creating a table name, Amazon Reviews Parquet. And then what we can do is we can write a SQL query, which you can see here, which will define this schema. So let's see how this works. Now, I'll show you the printed command. It's easier to read. So we're doing a create external table. This is a SQL statement. The database, we're just using the default and defining a table called Amazon Reviews Parquet. And here you can see we're putting in the marketplace is a string, customer ID, a string, review ID, a string. So this is the schema of our data. And we can say it's partitioned, and the partitions come due to the fact that it's Parquet data. So this one is partitioned by the product category, which is an optimization. If we do a lot of queries where we do, for example, where product category equals, this is a good indicator which column you could use to partition the data. And just giving it a little bit of more information here. And you can see the location is pointing to an S3 bucket that stores this information. And again, this is just creating the schema. So we know how the data looks and we can run the SQL queries then. All right, and we're running this command through the pandas read SQL here. So we're passing in this statement and the connection objects, which sets up the connection to the Athena service. All right, and we just need to load the partitions, and this is just another SQL command here specific that we need to run, msdk repair table. And then we can run another SQL, show tables in the database, and we can see here that our table got created. And this is it. So what happened here is we created the metadata, the schema information, in a data catalog service, which is used by Athena. So you didn't even have to specify it here. It is AWS Glue, if you're curious. And we will also see a link here in just a second how this looks like. And we can use this schema information in the catalog now to run SQL queries on our data that is sitting in S3. So for example, let's do a select star. Select star from this table where product category equals, let's say, digital software, and it's limited to 100. And you can run this command again here with the pandas read SQL query and do a quick head. So we're looking into the results in the pandas data frame. And here you can see how the data looks like. So product reviews data, giving information about marketplace, review IDs, product IDs, etc. And what we're going to be interested in later on is the review body. This contains the actual review text and also the star rating, which is a rating from 1 to 5, 1 being the worst, 5 being the best. All right, so we can query the data. Again, it's sitting as Parquet data files in our S3 bucket. All right, and the rest here really just makes sure everything is set up correctly. And here is a deep link. So if you're curious how this data catalog looks, you can click on this link. And this takes you back to the console and to the AWS Glue service. Glue, some of you might know, has been pretty popular for ETL jobs, so extract data, transform, and load data. But it also comes with a data catalog component. And this is actually what we're using here. And in here, you can see this default database that we used. And if you look at the tables, you can see here this Amazon reviews per K table that we created. And if you click in here, you can see it's pointing to a location in S3. So this is our bucket where the data lives. And all that it carries is the schema, right? So saying the marketplace in there is a string, product category is a string, and star rating is an integer, for example. So this is really a catalog that's helping to keep the inventory of the data and then enables Athena to run those SQL queries. And again, there is no database involved, right? The data is sitting in an S3 bucket. And this is the big difference, Redshift being a cloud data warehouse where you have very structured data, Athena being an interactive query service to really run SQL queries on any size of data, could be petabytes of data sitting in an S3 bucket or data lake. All right, so this was the second notebook here to register our data. And we can use the data now in the next step. So if you open up 03, visualize reviews dataset, here we're going to show you now how you can use the integration, so Athena, to now really explore the data and also visualize the results. And then just a quick peek here, what's next? Next, after this, we're going to run analysis on the data to analyze if there's any statistical bias, imbalances in the data. And then after that, we're probably going to have a break and then start with the model building. So we're going to explain how to prepare the data, the features for the BERT model, introduce you to the BERT model if you're not familiar, showing you how to do the fine tuning, and then start into the pipelines as well. All right, so before we get there, let's have a look at the data and explore it a little bit. So if you open up 03, do me a favor and also do a restart kernel and run all cells to get the notebook running here. So this notebook is actually pretty long. So we're doing a lot of visualizations in here. I'm not going to show you all of them, I guess, in the interest of time, but just going to introduce you what we're doing in here. And then you can poke around a little bit longer, maybe in the break or after the workshop here. All right, so we want to visualize, explore the data, as I said. And again, here's a quick review, quick recap of the columns. We're going to pull in here again, just the little setup here. So pulling in SageMaker SDK, the AWS Python SDK, both 3, setting up those variables that we might need, the bucket, the role, the region. And then here we're pulling in NumPy, pandas, and Seaborn, and matplotlib, because we're going to do some visualizations. And also, if you're working on a MacBook, there's actually an optimization to render the figures here, the visualizations, the plots, optimized for a Retina display, which is pretty neat. And you can also see here we're using the Jupyter Magic Store command. So we're retrieving a value and checking if you've executed the previous notebook correctly, because we will need to have the schema defined and registered in the data catalog. So we're checking here if this variable is set, which gets set in the previous. And as long as you don't see any prints coming out, or the print says true and okay, you're all good. If the cell prints the error message for you, then you've probably not waited for the previous notebook to finish, or maybe have not run all cells. So let's assume you followed, run everything. You should see true and okay. And again, if not, just run the previous notebook. And we're using, again, the same database name default and the table name Amazon Reviews Parquet, pulling in the PyAthena client, using our query cache bucket to store the query results, setting up the connection to our region. And I'm setting some seaborn parameters here. And again, seaborn, matplotlib are visualization libraries you can use in Python. And here I'm just setting some overall parameters like font styles, colors, grid line styles, etc. Nothing too exciting. And I do have a little bit of helper code to show values on a bar plot that I'm producing here in just a second. All right. So what we're doing in this notebook is we're asking a couple of interesting questions to explore. And for example, the first one here, which product categories are the highest rated by average rating? So how this works is I'm first generating a SQL statement to give us that answer. And then we're seeing the results, and then I'm visualizing this. So for example, this SQL query here, pretty straightforward. Select the product category, calculate the average of the star rating from this table, again, which points to the data still sitting in S3. And then we're doing here a where product category. So we're just limiting it here to the 3 categories. The data set has 150 million reviews, so we want to just limit it a little bit here so the queries execute faster. So let's execute this on a subset of the data and group it by product category and order it by the average star rating descending. And this gives us the answer here to our question. So we'll execute the command again with the pandas read SQL statement. And you can see here the result in this table. So gift cards, for example, has an average star rating of 4.73, pretty high out of 5. Digital video games, not so much, comes back at an average of 3.85. And digital software at an average of 3.53. All right, so I'm just making sure here I keep track of the number of categories. And then I'm visualizing this as a bar plot. So bar plots are pretty easy to produce. It's built into the Seaborn library. So I can just do an SNS bar plot and give the description for the axis and the data frame that holds the results as the data points. And then I can do a little bit of optimization here on figure sizes, depending on how much categories we queried before. Setting titles, setting additional descriptions here on the x-axis, and calling then the PLT show the bar plot. This is just how the matplotlib code works. And you can see here the visualization coming up. So pretty nice. Maybe not too exciting with only the 3 categories, but what we put in a screenshot here that shows the results if you run this across all of the categories. And what you can see here is that, for example, the gift cards are indeed the highest rated category with 4.73. And all the way down, digital software is indeed the lowest average in the star ratings here. So software is always a tough one, I guess. All right, and we're running a couple of more queries here. I think we have 10 or 11 queries here in this notebook. For example, which product categories have the most reviews? Again, this is pretty straightforward here in SQL. So you're just doing, instead of the average, now a count of the star rating, and then also order it by the count descending and group it by the product category. And this is showing you here, we have 149,000 reviews for gift cards, 145,000 for the video games, and 102,000 for digital software. And this is helpful if you're building up your training data set and you need to understand how many samples do you have, right? Maybe for the first exploration, when you're starting to develop your model, you might need just a smaller data set to explore and experiment quickly. And then as you're building out a little bit more detailed, you know which algorithms to use, etc. Maybe bump it up to higher training sets than for the final model trainings. So giving you a good indication here for us, definitely for this workshop. So we're going to use those 3 categories, which is giving us here roughly the 300,000 400,000 samples. All right, we can visualize this again. So I'm doing here another bar plot, similar here in the code. And then here we can see the results of the counts. And also, just to serve the curiosity, we put in a screenshot here. You run this SQL query on all of the data, which you can do. It just takes slightly longer. We can see books have around 20 million reviews, and it drops down pretty steep here for the other categories, which is also obvious, as books have been the first category when Amazon.com launched. So there's definitely over the time more reviews available. Then maybe if you go down here to major appliances, personal care appliances, etc. All right. And we have many more reviews. Again, I'm not going to touch on each and every one, but for example, we asked when did each product category become available? And that is really just a rough estimate. So the reviews contain the first year. So when the first, it doesn't contain the first year, it contains the year of the reviews, I should say. And we're actually looking for the oldest, which then is the first review year. And this we're just using as an indication of probably when the first review came in for gift cards. That's roughly the time probably gift cards got introduced as a category, right? So this is what we're doing here. And we can visualize this, and here's just another plot. So here I'm doing this line plot here, so you can see here, for example, showing the different years and when each category got introduced. Here's just a count of one category in each year. But again, if you're plotting this across all of the reviews, you would see here a spike. Actually, 13 different categories return 1999 as a first review year. So it could mean, for example, that those categories got introduced in the year, or it could be just the data set, how it is constructed. All right, you can do breakdowns of ratings, for example, per product category. And I'm just going straight to the visualization here. It's a lot of code. But this one here is kind of an interesting one. So here you can see the distributions. So the green here is the distribution of 5-star ratings. The yellow is the 4-star ratings, and so on. And red is the 1-star rating. And you can use that information for a baseline to detect how the distribution of those labels should look like, right? So let's assume you have your model deployed, train deployed into production, and you want to observe if there's a drift happening, right? So given this baseline of enough data, you can fairly say that normally pretty much 85% maybe of reviews in the gift card category come in with a 5-star rating. So if you suddenly detect that your model is predicting 50% 1-star ratings in the gift card category, that would have a big impact, right? So you can say, well, this is drifting enormously from this baseline, which normally happens. So running those queries here can really give you kind of a good understanding of how the distributions normally look like on the data you had until now. And if anything drifts later in real time, it's a good indicator to double check if there's a drift happening, maybe in consumer behavior, if there's an issue with the products, the reviews come in, etc. All right, you can run this here across the whole data set, and here's a screenshot, and you can see the distributions here changing accordingly. All right, how many reviews per star rating? So we have a bunch of more queries in here. And the observation here is we have way more 5-star ratings than we do have 2-star or 1-star ratings. And again, this gives you a good indication if your data set is balanced or imbalanced. And I guess this is easy to spot. If you're training the model with this data, the model will pick up on way more 5-star ratings and might also pick up to predict way more 5s than 1-star ratings. And we want to have the model predicting really based on the review text and not so much on this distribution, right? So there's definitely some actions for us to do. And we will show you this in the next notebook when we're analyzing for statistical bias. All right, I'm scrolling a little bit faster here. We do have a lot of visualizations if you're interested in how to create those. One of them is, for example, plotting the average star rating over time, which gives us this line here. Or what else do we have here? We can do it per category, and this will give us a crazy number of lines. But also you can see that a few categories really dropped in the average star rating over time. So if you're, for example, the business owner of that product line, that would give you good indications to definitely have a look what happened there. All right, which star ratings are the most helpful? And it's funny enough, most people rate the bad reviews, the 1-star ratings, as being more helpful than the majority of the 5-star ratings, which I guess is also obvious. We also want to know the catches, right, when we're looking at a product to buy. All right, yeah, there's a couple of more. I just scroll through here. I want to show you the last one in here, because this is actually one we're using in the model development workflow. So the last query here, I'll scroll up to the question. What is the distribution of review length, the number of words? And this is particularly important if you're building this NLP model, which we're doing, the BERT model, because you need to define a hyperparameter, which is the maximum input sequence length. So the maximum number of input tokens, and we're going to explain what a token is and everything in a bit. Think of it as the number of words you're sending to the BERT model in one sample to then do the prediction, right? In our case, do the classification. So how many words does a sample review have? And it's a parameter to train the BERT model on. And to get an understanding which parameter, which value is a good one, what we could do is we can calculate this distribution. So this is what we're doing here. So select the review body, which is the review text. We're splitting it by space, so we get the individual words. And then we're doing the cardinality, which is giving us the number of words. And I'll show you here now the plot, and this becomes a little bit more intuitive then. So if we're plotting this distribution, we will see that the majority of reviews have around 64 words or less. And you can look at the table here, which has the exact numbers. So the shortest review has just 1 word, which could be okay. And the longest review has more than 5,000 words, right? But if you calculate the percentile, which we're doing in here when we're describing this result in the data frame, just clicked out of my studio here, sorry. You will see that 80% have 63 or less. Sorry, just need to scroll back down here. Here we go. So 80% have the 63 or less. So what you could do to select a good value here is probably around 64, right? Because it's a very long tail here, but it's really just a few reviews that have longer. And what will happen is that in the model training, you will truncate all reviews that have more than those 64 if you set the parameter. And if you have reviews coming in shorter, you will pad them up to that length. And again, we will explain why this is important here in the notebook when we're getting to the BERT model. But again, this is one way also here to run data exploration and get good insights for parameters that you might need in the actual model hyperparameter settings. All right, and then the last cell here again, if you run that, is shutting down your kernel. All right, so yeah, checking in with Chris here, how are we doing? I would probably do one more notebook that detects statistical bias and then give everyone a break, unless people are already asking for a quick break here. Yeah, any questions, Chris?
Yeah, I think I think I covered everything. Some questions around why would you use PyAthena versus AWS Wrangler, which we tend to get a lot. Yeah, PyAthena is obviously just Athena. AWS Wrangler crosses many different services, so you can actually import and export data between Redshift and Athena and S3 and certain databases, and even had Spark support at one point, which I think was dropped in favor of other more full-featured Spark support throughout SageMaker and EMR. A couple questions about how long, or one question about how long would it take to query the 150 million reviews? Do you remember? We did that a while ago, just a full table scan.
Yeah, it actually depends on the queries, obviously, right? How complex the queries are. It could be, yeah, it could be just a few seconds really for the simpler queries. It's not too much more. But this cardinality, the last query, that just that takes very, very long. Because you're literally counting the number of words in each review. And if you're doing that for 150 million, that is just a very intense query.
Yeah, that's the extreme, where we're actually counting every character of every review, which I don't even think ever finished for us properly. Not on the full data set, but you know, normal aggregations, if you're trying to average the star rating across all 150 million. If it's in Parquet, it's probably 1 or 2 minutes at this scale. If you're doing a full scan, it's, well, yeah, but then it still depends, but it's on the order of minutes. There's another question. Okay, let's see. Something about, is there a specific reason behind the values of 8 on the num words chart? And I don't know how to answer that.
Let me see, the 8.
So I think num words would be the very bottom, the very last one, right?
Yeah, sorry, yeah, scrolling down. It's a long notebook here. I'm not sure about the 8, I guess the 80% maybe?
80%, right. Is there a specific reason? Yeah, go ahead.
Yeah, and we just picked that randomly, right? It's just like looking at the numbers. You can see, you could also have chosen maybe to capture 90% of the data, right? We're just calculating those percentiles.
Yeah,
and looking at the results.
It's not chosen randomly. It's chosen because we want to capture that it's okay for us to capture just like 80%, right? You know, very rarely do you want to capture the full long tail. And Ansha, can you scroll and show the chart a little bit more? So here we see things, you know, really, really trailing down. We probably could, in fact, like when Ansha and I first did this, we chose 128 because we wanted to capture more of the long tail. We actually did a hyperparameter tuning sweep where we did it at 64 and had similar results. And if you go higher, so you have to pick power of, oh yeah, this is actually getting ahead of ourselves a bit here, but the more data that you look at, it might not benefit your model. And so we'll explain that a little bit, how BERT works. BERT forces you to choose a power of 2, or it really strongly encourages power of 2 for the number of words in your review or in your text. And so here it's pretty clear that we would either use 64 or 128. We could have used 256, but every time you go higher, you're going to use more memory and more CPU. I mean, you know, down to the systems level, your buffers are 128 long or 256 long. And we want to keep that down so we can train quicker, we can train more cheaply. And we chose to capture the 80th percentile because that was good enough for us in our empirical testing. Do any of the labs cover autopilot? I will send the link to the autopilot labs. That's in our full 12-hour one, which we're not doing today, but we have, the book covers it very heavily. And here, I'll actually just paste the link right here. So we're not doing these. Yeah, and then Arnaban, Anirban says the classic 80-20 rule, which can be applied here. It's a business decision. Here's autopilot. Don't run these today. You can run them offline for the autopilot, but it's all coherent and all uses the same data set. And yeah, everything in the book is one pass through and then doing it all these different ways. There's a comment here that says, do you mean the wrong classification? A bug maybe. 916 AMPT VJA VJ. Any comment there, Ancha?
Let me see if I find the comment. I'm not exactly sure.
You mean wrong classification? Okay, which notebook were you going to do next?
I think we can do a break. I think we're doing pretty okay in time. So maybe we can do maybe a 10-minute break, and then I'll do the analyze for statistical bias, and we can jump into the feature engineering.
Okay.
Shall we do 10 minutes?
Yeah, let's do, so it's 9:30. Let's resume at 9:40. Resume at 9:40 a.m. PT, 10 minutes from now. Pause your screen, Ancha, and let's take a break. Yeah, and I'll keep answering questions here. Okay, welcome back, everyone. Just a reminder that if you want to reproduce this workshop after today in your own account, the 00_ quick start would only cost less than $2. If you wanted to reproduce the entire book, which is every single section under workshop 01 through 12, it would cost less than $25. So good questions. Just be clear that and make sure that you tear down any resources that are created. So we've seen that before where we do workshops, and that's the other reason why we don't want to do it in your specific account today, is we don't want you to incur any cost at all, and you can selectively choose what to work on your own time. Alan, comprehend. So comprehend creates a SageMaker endpoint, and the endpoint runs 24/7 as a feature. And if you don't know that, it'll cost some money. Alan, if you haven't already, contact support and explain to them your situation. As a consumer on the external side of the AWS firewall, I was in all of your shoes, and had run up some bills unexpectedly, and support was very happy to work with me, and just had to justify it, and they took care of it. So okay, Ansha, are you ready to roll?
I am ready to roll again. Yes. All right, and I see the comment here. If I can do a quick walkthrough of SageMaker Studio, we can certainly do this here as well. So yeah, let me pick up here. So quick recap. In the first part, we showed you just how to set up the dependencies, but then we also ingested our data set. So we connected basically the data that is already sitting in S3 with the Athena service. So we registered and cataloged the data, created the schema information in the data catalog in AWS Glue. And then we used the Athena service here through our notebook to run queries on the data, and we visualize the results. So what I'm going to show you next, just going to shut down here the kernel of 3. If you open up 04, it's getting exciting. So we're going to use a new functionality that is part of SageMaker called Amazon SageMaker Clarify, which got released at last re:Invent conference in December. And with Clarify, we can analyze the data and also the model later for statistical bias, imbalances, etc., and also run model explainability. So quite some exciting new capabilities here. Let's maybe run this notebook, and then I'm going to also do maybe a quick overview here of Studio while the notebook is running. So again, I'm doing a kernel restart and run all cells in here. And just make sure here, yep, so it's starting to execute. Quick recap before I jump into the Clarify. Studio here, as you can see, is pretty much based on the Jupyter Hub environment and Jupyter Lab environment. And you can see the navigation structure here on the left. So the top one here is the file browser, which we're going to use here to go through our notebooks. The second one here is giving you a direct Git integration. So we're operating in a GitHub repo. So you can see here the Git commands, so the branch you're working in and changes. So if you're working actively from GitHub, you could also use this environment if you like to stage and commit. The third one shows the active kernel sessions. So don't click around here and stop them. But just to show you also, because people were asking where the store magic is stored and everything. So we do have underlying instances. And one instance is powering Jupyter. So you can see here it's running on the MLT3 medium instance. And this is basically where we're storing all those magic commands, these key value stores locally. So this means if you're releasing a notebook kernel, we're not losing that information. The notebooks are running on top of the underlying compute infrastructures. So for the different kernels we're choosing here, as you saw, we're choosing the Python 3 data science kernel, which is again powered here by an MLT3 medium instance. And yeah, in general, you want to keep track of those for housekeeping purposes. So you can see here what is running. And basically, in terms of also important to know what is causing cost in general, you're not paying on a per notebook, you're paying for the actual compute instances that are running. So now and then, it's always good to check what is running. In this workshop, don't close anything, don't click on those shutdown buttons. Otherwise, it will take a few minutes again to bring them back up. So yeah, don't kill them right now. Yeah, and then the rest is here a little bit of normal Jupyter Lab environment. What we do have extra is the bottom 2 navigation items here. So the second to last one here is an integration to a capability called Jumpstart. And in Jumpstart, Studio gives you access to model hubs, specifically to the PyTorch hub and the TensorFlow hub. So where you can find pre-trained models. And it also comes with end-to-end solutions that AWS built for specific industry use cases. So if you click here on this Jumpstart, maybe just in between when you're waiting for notebooks to complete, you can see those solutions. Again, those are end-to-end environments for common scenarios, let's say fraud detection in financial transactions, predictive maintenance, etc. And those will actually deploy all of the service integrations, will give you sample notebooks, and give you a complete environment here to start working in those use cases. And also, as I said, it works with PyTorch Hub and TensorFlow Hub. And you could, for example, use those pre-trained models and pull them in and deploy them here straight into the AWS account. So pretty nice. And the last menu item gives you additional navigation to specific environments here. So for example, we're going to see this when we're getting to the pipelines. We will see then our pipeline, which we're going to create, showing up here. And you can drill down further. It gives you an overview of the current endpoints you might have deployed, the model registry, which we haven't gotten to yet, the feature store, etc. So this is just really additional navigation, and we will show you part of that here when we're getting and actually filling up a little bit of those here during the workshop. All right, back here to the 04 notebook. So yeah, if you run this notebook, this will now start an analysis on our data specifically to detect statistical imbalances. And the topic of bias and explainability is a very broad one, right? And heavily in research and discussed in the industry. And it could probably fill a whole day of discussion. I've put in here a paper if you're interested in learning more. This is a paper from the Amazon Science team, which regularly publishes new research and new great stuff. And they've also published an article here on how the SageMaker Clarify tool can help machine learning developers to detect unintended statistical bias in data in model and run model explainability. So if you want to read maybe after the workshop and familiarize yourself a little bit more, that's definitely a good paper to start. In general, to talk about the bias and understand what it means, there's a little bit of terminology to get familiar with. And I put in here kind of the important terms you need to understand. So when we talk about bias, we're talking about an imbalance in the training data or the prediction behavior once we deployed the model. And this will happen across different groups, different columns in your data set, right? And we want to make sure that the model doesn't treat specific columns in the data set different, right? And I mean, this is easier to understand when we talk about maybe humans or income data. But it can also happen, right, if we're talking about the product reviews that we're touching on today as our data set. So I showed you before that the gift card category has way more 5-star ratings, right? And this is a statistical imbalance in the data. So the model could pick up and just, favor gift card ratings way more because it knows that it will produce, the 5-star ratings. And this is what we want to analyze, right? So to analyze for imbalances, we can leverage bias metrics. And bias metrics are basically mathematical functions that you can run to calculate values that will give you a good indication of whether there is an imbalance. And then those results are coming back as a report if we use Clarify. And another important term here, label is pretty straightforward. So label is the target that we're training the machine learning model on. In our case, the star rating is the label. And the positive value is the value of this label that you want to analyze if there is a favorite column or a favorite group in the data set to achieve this. So in our case, the positive label value would be the 5 for a 5-star rating, or a 4 maybe. If you're running maybe college submission predictions, a yes, I get submitted to the college would be the positive outcome, and a no, a decline would be a negative outcome, right? And the other term to understand is a facet. And think of facet as a column in the data set. For example, the product category. And the facet value would then be one value of that attribute. So for example, for product category as a facet, the facet value could be the gift card, right? All right. And then we need to understand the metrics. And again, I put in a link here to the documentation, which you can maybe read if you're interested in understanding those metrics more. There's a lot of those functions that you can actually use to check for the imbalances. And an easy one to understand, I guess, is the class imbalance, CI. And you will see here also the formulas, how this gets calculated. So there's no magic. It's really all coming down to math again. So for the class imbalance, you're looking at the number of samples for one facet value. And again, facet value is a value of a column. So let's say gift cards, number of samples, minus the number of samples of all other category values in here, and divided by the number of samples plus the number of samples of all others. And this gives you the class imbalance value. And in general, if the result is closer to 0, that means a more equal distribution. If you're having a positive value that means in this case, the first facet value here, for example, gift cards had more samples. And if you have a negative result, that means it had fewer training samples. So this is how you can understand those metrics. And there's a detailed description here of all of those: difference in proportion of labels, Kullback-Leibler divergence, etc. And as you can see, the formulas get a little bit more complicated, but here's a description and also advice how you can understand the results. All right, so the good thing is Clarify will calculate all of those for us, so we don't have to do the math ourselves. And let's see how this is done. So again, I'm importing here the libraries, Boto, SageMaker, pandas, NumPy, set up the environment, also matplotlib to visualize some of the data sets so we can see the imbalances. And what I'm doing here is I'm picking 3 categories again. And here you can see I'm using the TSV data as the machine learning normally uses the row-based data sets. So this is tab separated. So I'm reading in the gift card reviews, the digital software and the digital video games. And I'm just doing this here to demonstrate just a subset of data and show you how the data looks. So I'm concatenating this here in a pandas data frame. The data still looks like we saw before. But the interesting part now is if I plot it here, you can see what we've seen before, that even all of the 3 categories together, there's still a high imbalance in the number of samples across the different categories, but also between the star ratings, right? In general, way more 5-star ratings than there's 1 or 2-star ratings or 3-star ratings. I guess nobody likes the 2-star ratings. So we can spot right away in this case that there is an imbalance, right? So let's use this. So I'll import, or not, sorry, I'm uploading this CSV file to an S3 bucket so I can access it from the SageMaker environment. And next, I'm showing you how you can use this new Clarify tool to analyze for the statistical bias here. And first thing, I'm just generating here an output path where to store the results. And I've already defined where I store the input. So this is the CSV file that I uploaded to this location. I'm giving in this Clarify data configuration also the output path where to store the results. And I need to define the label. So in this case, in the dataset, the star rating is the label. And I'm giving it also here the list of headers for the other columns. And I'm specifying the data type. In this case, it's text data CSV. And this will define the data configuration. So I know where to find the data and what the label column is. Next, I'm defining what to analyze for. So I need to define this bias configuration a little bit more. And in here, I'm setting, for example, the positive values. And again, if it's a binary classification, it might be a yes and no, maybe for college admissions, etc. In our case of the star ratings, the positive would be the 5 and the 4. And the facet name, again, is the column. So in this case, we're analyzing the product category. If we favor any product category, and group name is used for one particular metric, which we're also just setting here to the product category. All right. And next, this is where we're going to use now a construct of SageMaker, which is a processing job. And processing job is the ability to execute code on our data set. And what happens is SageMaker will spin up instances, and you can define them here. So you can define a compute instance type and the number of instances. So in this case, we're using 1. If you have a lot of data you need to process, you can change the type of the instance and also do maybe in parallel. So you could do maybe, I don't know, 5 instances in parallel. And then SageMaker will start those instances and will run code that you provide. In this case, there is already a type of the processing job that comes with SageMaker Clarify, hence you don't have to provide any extra code. But you could also use the general processing job, for example, to run feature engineering. And this is what we will do in the next notebooks when we're building up this pipeline. So processing jobs spin up managed compute instances and execute, for example, data pre-processing transformation code you might want to run and do things like this. We're using a special implementation that comes with a clarified code here. All right, and then we can, on this SageMaker Clarify processor, we can simply call run pre-training bias, and then passing in the data configuration, the bias configuration. You can specify which metrics to calculate. Here we're just doing all of them. And this will start in the background now, those compute instances which we specified, and execute the analysis. And we put in here a link if you're curious to the processing job. And this will take you again to the console. And you can see here, this is the SageMaker environment. In the left menu under processing, you can find all of the jobs, the processing jobs that are running. And the notebook will actually start too. So the first one here that I just introduced does this analysis on the data set. And you can see here the inputs. So here, for example, the input data set that we specified, and also where the output gets generated. All right, so let's see, what else do we have here? If you're curious to analyze really anything, the logs of all the jobs, not just the processing jobs, but also later on training jobs, for example, or your model endpoints, pretty much all of the logs end up in CloudWatch. So here's also a link where you can check for anything that's happening inside of this processing job in this container, basically, which is running. So here is the log stream in CloudWatch. And here you can see if you need to troubleshoot anything, you can see what's happening in here. All right. More interesting is the resulting outputs. And we specify the target where to write the results. And we also put in here the link to the S3 bucket. And you can see here, if I zoom in, that here is the bucket, and Clarify generates here the configuration and the resulting report, the bias report in HTML as a notebook file and also as a PDF. So I bet you're curious now to see the report. And we're downloading it here in the notebook, which is a little bit easier than you can also pull it from the S3 bucket. We're doing it in the notebook. And then you can just click here to see the bias report for the unbalanced data, which we provided. So if you click here, you can see now the results, and it summarizes nicely here. The star rating was the label, and the positive values were the 5 and the 4. And we analyzed the product category as a facet, and it runs now the analysis. It calculates the metrics for each value it finds. For example, we had 3 categories: the gift card, the digital software, and the digital video games. And you can see here pretty much all of the metrics come back with a value either positive or negative, but it's not really 0 unless the first one here. So we can see that there is an imbalance. And again, the closer it comes to 0, the more balanced the data is. And the higher it goes to either the +1 or the -1, that means the more it is imbalanced. So we can see here all those metrics indicate we do have a job to do, right? So what we can do here, in our case, pretty simple. So what we're doing is really just making sure we have the same samples, the number of samples across all the product categories, and also across all of the star ratings. So we're basically sizing down or sampling down to the minimum number of samples. And this is a technique called downsampling. So we're looking at what's the minimum and then just making sure all categories have that minimum. If you don't want to lose training data samples, which we will in this case, you can also do an upsampling where you generate additional data to fill up to the highest watermark. In this case, we're just doing the downsampling for easiness. It's not quite trivial to generate text data. So in this case, we're just going the easy path and cutting it down to the number of samples here to make it equal across all of the different classes. All right, and you can guess what's coming next. So we're again uploading this balanced CSV file now to an S3 bucket with this upload command. And then I'm running the same Clarify job on this new balanced data and see what the results are. So again, the data config shows now points to the balanced data, which I uploaded, and providing an output path, still the same label, star rating, giving it a column header list and saying it's text CSV data. And the bias configuration is the same. So 5 and 4 are still the positive outcomes in the star rating prediction. And we're analyzing the product category as the facet. And again, we're starting our Clarify processing job, instance count and instance type. And again, you can run this on really any amount of data, right? So imagine you have maybe terabytes, exabytes, maybe even petabytes of data sitting in your data lake. You can simply increase this instance count here, instead of 1, do a 5, do a 10, do 100, to run this analysis in parallel on your data. So it becomes powerful if you have to scale out. And this is really kind of where the flexibility and agility of the cloud instances come into play. SageMaker will manage those, start them to do the job. And once the job is completed, it will shut down those instances. So you're only paying for the time that instance is actually running and processing and doing its job. All right, so we run the pre-training bias again, passing the data. And the same thing happens. So again, it starts this second processing job, which you can see in the console. And those are pretty fast. The CSV data is not too big. So you can see here my jobs took around 4 or 5 minutes to complete. So again, we have a link to the CloudWatch logs if you're interested to see the container outputs. And I'm going down here to see the report. So we want to see what Clarify comes back with. And here we go. So you can see now that the values switch to a 0, which means the data is now balanced. Right? We did a super balancing of the data across everything. So we see this here in the 0. And if you wonder, the class imbalance shows a 0.33. And this is because we passed in 3 categories. So if you add them up, it's 100% of the data. So it is balanced, but from the viewpoint of a third of the data from the individual class, it looks like, no, it's a third of the data. But again, this means it is balanced. If you would have here 2 classes, it would come down to 0.5. And if it's, just 1 class, it is fully balanced. All right, so this was a quick intro how to use Clarify to analyze the data before you're starting to train the model. We will also see later, once we've built the pipeline and trained the model, how you can use Clarify to analyze the trained model for any imbalances in the predictions, and also how to run the model explainability to see which input features do have the most influence on the prediction result. And this is also coming from SageMaker Clarify, that support. All right, so this was the first part of the workshop. And I will hand over now to Chris, and he will show you now how to start developing the model. And we're going to start with an introduction to the BERT model, which you're going to use, and how you can prepare the text data that we have into the features that are expected by the BERT model. And then go along the pipeline, introduce you to the fine tuning, and then build our SageMaker pipeline. So checking in with you, Chris. Are you ready?
Yeah, I got these going. Let's see, 5 and 6, right? Okay.
Yes.
And people were asking, to see more of Studio. We'll show it in these next couple sections because we're going to be building pipelines and populating feature stores and doing all kinds of fun stuff. So we'll be registering models and deploying endpoints and actually making predictions. So all of those we'll see, I think. Okay, the Slack is full of questions on balancing data sets and Clarify. So can you handle those, Ansha?
Yeah, I'll have a look.
Take care of those?
Yeah.
Okay, thanks. All right, let me flip over here, grab the screen. Looks like DA is asking about any caps on how many jobs we can run, processing job limits. There are limits, mostly to prevent, fraud, things like that, or just to be able to do, on the back end capacity planning for all of these cloud resources. So yeah, Ansha can talk about the limits. She and I are very familiar with the limits from our work. We hit them while we were writing the book, even when we were scaling up. For the book, we actually trained on a P324 or P424, which they're monster GPU instance types with eight GPUs on each instance and all kinds of stuff. All right, so Ansha, should I do these two? We'll start the pipeline and then take a break, right, during pipeline?
Yeah, and maybe, let me see on the time. I think we're actually doing pretty fine on the timing today.
Yeah, it's 10:10. So we're 2 hours, 10 minutes in. Yep. Okay, so if you would start up O5. So jump into O5 here and actually clear out. Oh, I actually wanted to run this one. So that stuff about the 80% and the 63 words captures 80 percentile of our data set. That's going to come in handy here in a bit. So let me get this data in there. I actually forgot to run that notebook, and then I'll run O3 here in a bit as well. So O5, so this is where we're actually going to convert our text features. So with machine learning, we need numbers, we need vectors. We need something that can be mathematically represented so we can perform mathematical operations and vector math and linear algebra, our favorite course from university or high school. So what we're going to do, the very first step, because we have human readable text, we need to get it into machine readable numbers to do this transformation. So this is possibly called feature transformation. You've typically done this probably with Scikit-Learn, where you've done one-hot encoding on categories and fun tricks like that. And in fact, I have about 3 feature engineering books that I'm behind on that I've picked up over the last year because I was writing so much I didn't have as much time to read. But feature engineering really is where you will in the future will likely come in to be the most handy. These algorithms, they're pretty much standard. They're very well studied. There's a lot of academics out there. There's a lot of big companies, Amazon, Google, Facebook, that are releasing very powerful algorithms. And really, we don't have to worry about those anymore. There's a famous quote by Andrew Ng, co-owner of Coursera and Deep Learning AI, or founder of those companies, co-founder of those companies, who basically, I'm paraphrasing. I don't have the exact quote here, but something on the lines of, you should be spending more time feature engineering than focusing on new research for these algorithms. That's really where most of us should be in our practical data science lives. And also there's pre-trained models. So BERT is technically considered a pre-trained model. And if you come from computer vision background, you've seen pre-trained models before. You've seen ImageNet, right? Like you've seen these models that have learned how to detect edges and learned what a face is, and learned what a stop sign or a stoplight means. And we want to reuse all of that information, but just fine tune it to our specific domain. And so where this comes in here is, we're going to use a pre-trained BERT model that has been trained on millions and millions of Wikipedia documents and Google Books corpus. Yes, if you recall, a few years ago, Google Books, Google started scanning in books, and they got into a little bit of trouble. I'm not going to go into those details. There's actually a really good documentary I just watched, either on Netflix or Prime Video, that goes into all the details of the sort of legality and the public, which books are public domain and which ones are not. But the short of it is, they scanned in hundreds of thousands, if not millions, of books, and have trained language models, which of course they use for search engine, they use for serving ads, they use for everything. But all of that knowledge, which translates into weights in our BERT neural network. So BERT is a ginormous neural network, has millions, billions of weights that define that network, that neural network. And we're going to reuse all that and just pass in a really small set relative to those millions and billions of documents. We'll pass in just a small set. In fact, our training runs for only about 30 minutes, and I think we get close to 70–80% accuracy. We'll use our domain, which is our customer reviews on products, and we will train and fine tune this pre-trained model so that we can classify into star rating 1 through 5. So that's the end goal, is to classify documents, basically form of sentiment analysis, but we're doing multi-class, so it's not just positive, negative, it's 5 stars. And so we can, with pretty good accuracy, predict whether a review is going to lead to 5-star, 4-star, 3-star, 2-star, 1-star. So that's the end goal. But to get there, we first need to convert our raw text into the BERT vectors, or the embeddings as they're often called. And really, so these embeddings, this term is generic. It's beyond natural language. It's actually one-hot encoding is a form of like the embeddings. And yes, images can be converted, yes, into these same embeddings, vector spaces. And there's actually whole companies. I've got a friend here in the Bay Area who his whole company is just creating embeddings for video, for sound, for anything. Basically, yes, embedding as a service, if you will. So very powerful. And what we'll do is actually store those embeddings to be used later inside of our feature store. And so we can train off of the feature store. We can actually make predictions. So picture a user logging into Netflix, for example. That user doesn't really mean anything to the recommendation engine unless it's converted into some type of embedding. And so Netflix is just constantly generating embeddings 24 hours a day, running jobs, and they're creating multiple of these embeddings per user, based on time of day, based on where they're at. Maybe they're traveling. The traveling use case was always really difficult for us at Netflix, because not only did we have to work around or work within studio limitations. If I go to Germany and I want to watch a movie, I have to be bound by certain geo restrictions that the studios impose. And so Netflix ultimately has to code that in. But there's also, if I'm in Germany, maybe there's a particular huge event, maybe Oktoberfest is happening. And so, Netflix wants to know where I am so that it can start to make recommendations. Maybe there's a funny, there's this movie called Beer Fest that I love from many years ago, where I think they go to Oktoberfest, or they go to some festival. I think there's a couple of them. And so I want to see movies around what's happening, but they can't do that unless I am represented by some vector that can then be used to perform mathematical operations, recommendations, things like that. Okay, so that kind of sets up the context. What we're going to do is convert these raw TSVs into these embeddings. Also note that the star rating goes from 1 index, 1, 2, 3, 4, 5, to 0 index, 0, 1, 2, 3, 4. That's just how we're currently implementing it. BERT, so BERT likes things in this format as well, being 0 index. And we see that these input IDs actually represent the tokens. And so I'll talk a little bit about token versus word, but essentially one word in your review ends up being one or more tokens in the BERT vocabulary, as it's called. And these are called the input IDs. That's just what BERT calls them. And so I'll be sort of bouncing in and out of BERT specifics and higher level, just to continue to kind of bridge these worlds. Ansha loves this slide. It's called BERT, the BERT Mania slide. So there are many different variants of BERT. So BERT by itself, if you talk to an academic, BERT is an architecture. If you talk to a practitioner, BERT actually represents something specific to their domain, right? So there's kind of base BERT, right? But then there's German BERT, which is specific to a language. There's Camembert, which is specific to French. I think there's even one called Berto, which is the Spanish BERT. So people get really fancy with these BERT names. So there will be language-specific variants. There will also be domain-specific variants, typically within a single language, but sometimes crossing multiple languages. Patents, healthcare, scientific, bio. And so keep in mind, there's actually one called protein BERT. So proteins, protein sequencing is basically a language. And people have applied, in fact, one of our videos on our YouTube channel, we do a monthly webinar, which is actually happening in 2 days, where we'll have Hugging Face people on there actually. So yeah, tune in. But once you can actually represent language, you can, or something in the context of a language, right? So now you can start to model it and start to actually understand it. You can generate new sentences, so like generate sample reviews, for example, if you're trying to create more data. Oh yeah, there's Bertje too, which is Dutch. So similar to like Antje's name, A-N-T-J-E. If you add J-E onto anything, that seems to make it Dutch is what I understand. Okay, understanding BERT embedding. So BERT stands for bidirectional encoder representations from transformers. Transformers is the key architecture. If there's one thing that you want to actually dive into, it's this paper. The attention is all you need. Very fun name for the paper. And so what we're doing is we're passing in, I'll just kind of summarize this. We're passing in text, so that's at the bottom. So this is, I love this movie kind of thing. That then gets converted in the context of what has already been learned from these millions of like Wikipedia and Google Books corpus, or millions of clinical records or patent records. And then out comes, so we are basically creating BERT vectors, right? The embeddings from raw text. And so that's what you see at the bottom. There's a screenshot. Let me zoom in a little bit here. Hopefully, it actually worked against me, didn't it? Go this way. So yes, everything here will get passed into BERT. So this is the implementation details of BERT. And there's our label ID, which is the review ID 0 index. So, star rating. Yeah, sorry, not the review ID, it's the star rating. There's the review ID that is just the unique ID. So this is just sample data here. We'll show the real data here in a bit. But essentially, so in goes text, out comes a vector that's then used and passed into BERT. So that's what we're doing here today. In this notebook, we will automate all of this when we go to 07 and do the pipeline. But 05, what we're doing is just sort of showing you a very tiny version of what's happening inside of the pipeline that we'll do in 07. So 05, 06 are really just ad hoc is the term that like me and Antje use. It's running on even smaller data, very, very tiny data that fits in this notebook just to show you what's actually happening. Then we'll scale everything out in 07. So 05 is feature transformation, 06 will be training. Just doing a quick fine tune right in the notebook, but we can't scale it out too much because our notebook we keep small because we want to do all the like heavy processing on a beefier instance in our SageMaker cluster. Okay, here's some of the boilerplate here just to get access to the SageMaker, these like APIs and then Feature Store APIs. So let's actually dive in here. So Antje talked about Distill BERT a little bit. This is the lighter weight version. So this actually is a variant. In fact, we should probably add that to the BERT mania. So Distill BERT uses a statistical method called distillation. And distillation essentially is a student to teacher type of relationship. So you have a larger model, let's say the base BERT model, which is billions of weights. We want to distill it down and learn and train a student, a smaller student, if you will, less knowledgeable, but still pretty knowledgeable. So we're basically skimming all the best knowledge off of this full, billion weight BERT model, and then distilling it down into, I believe the distill BERT ends up being 66 million weights, which is much, order of magnitude smaller than base BERT. So, so this is good, but still retains 97% of the overall accuracy for this type of natural language processing task of multi-class classification. So we like Distill BERT. Not only can we run it on a small data set here in the notebook, right, like without crashing the notebook memory, but we can also use less CPUs, use less GPUs, and then ultimately save money. Yeah, in fact, yes, one thing me and Antje did for all, I think for pretty much all 12 chapters, maybe 9, or 10 of the 12, there's a section about reducing cost and increasing performance. And so each chapter has tips that are relevant to that. And this is certainly one of them, which is using pre-trained models. And then smaller variants like distill BERT. All right, so our data set, we've got the traditional fields that we've been speaking about so far. That's the actual review text called review body. Star rating is the actual label, 1 through 5. The rest of this really is just kind of Python code to, creating a class here, kind of nice little object-oriented way of writing Python code. What we're doing, basically, I'll just get to the interesting stuff. We're calling, so there's this library called transformers here. And this is by Hugging Face. And so Hugging Face, like you'll hear us talk about this, we actually have one of their people speaking on Monday, like I said. They've created a Python library that can do all of this stuff for us, that knows about all these different variants, has been highly tuned. They actually created the distillation variant called distill BERT. And so we can import it right here. Here's a tokenizer. Now this tokenizer is what's actually going to take the raw text and then convert it into those BERT vectors. And so that's really the heart of this whole notebook here is this call right here, which is passing in raw text and then getting out the BERT vectors. And here's the input IDs. This is input mask. I'll skip some of this stuff because either it's not used or it's more of an implementation detail that is meant more for a deeper dive here. But the token IDs, also called the input IDs, are those tokens that after Hugging Face transformers or BERT, when it transforms, it will parse all the words and then find any roots of those words potentially that are part of the vocabulary and then split them into potentially multiple tokens. So I'll show exactly what that looks like here in a second. It's definitely much easier to show than talk through. The other big thing that we're taking advantage of here is TF record. So TF record is short for TensorFlow record. If you were familiar with us talking about file formats earlier with Parquet and sort of different optimizations depending on what we're doing, such as querying, such as aggregating, here we are using a file format that is highly optimized, not only for TensorFlow, but also for row-based access, and specifically in the context of machine learning. And so this format is actually closer to CSV than it is Parquet, but it's highly optimized and it's binary and it uses protocol buffers beneath the covers, if that means anything to you or like you're interested. It is not human readable for the most part. I'll actually print one out in this notebook, and some of it's human readable, but most of it's not because it's binary, it's packed, it's compressed-ish, using run length encoding and all kinds of tricks. But just know that TF record is specific to TensorFlow. So when we do the PyTorch version of this, we actually don't use TF record because it doesn't apply. But just know it's that when we encode it into TF record, when we go to train, we will have to decode it out of TF record, which will show TensorFlow how to do that mapping, and then TensorFlow takes care of the rest of it. So if you're using TensorFlow today and not using TF record, yes, I would suggest trying it out. Might not make a big difference depending on how much data you have or what type of task you're trying to solve, but pretty much any high scale, complex modeling I've seen with TensorFlow almost always uses TF record unless it specifically doesn't help, which I haven't really seen any of those. Okay, and then don't forget that we also, because this is training data that we're creating, we have to create the label ID, which is again converting star rating 1 through 5 into 0 index 0 through 4. Okay, and all that then gets passed. Oh, so before we train, which will be the next notebook, let's show you how to actually store this in the feature store. So now some of you might ask, why do we need a feature store? Which is a whole topic. There's whole companies that are dedicated to this. This feature store feature actually came out during reInvent 2020, so just a few months ago. Major ask by lots of our customers. So feature stores might not make sense to you until you do a lot of modeling, until you need to travel in time, if you will. And perfect situation is, let's say Netflix, as pandemic starts to recover in different parts of the world, not everywhere, obviously, still quite a lot happening, bad stuff happening, but certain parts of the world, people are going back to watching Netflix in the old way that they used to watch, which might not be as much, let's say. So currently, I watch probably, like 20 hours of like Netflix a week because I'm bored and I can't go anywhere. San Francisco is starting to open up, but I like watching Netflix apparently. But when I go back to my old pattern where I actually leave my house and start to interact with like human beings, I'm not going to watch Netflix as much, or I'll start watching different things. And so Netflix may want to start training models as we start to come out of this, as though it was 2019, right? And not train as though it was 2020 or last few months. And so like the ability to sort of back up in time, this is used heavily by insurance companies, are always playing with time. And so you can do this on your own without a feature store. And most of us probably did or are still currently doing this, where you create a folder in S3 or on your local laptop and tag it with a particular date. These are all of the ratings and reviews and training data set as of this date. And sure, I can kind of go around and hard code and then hack it and back up to a certain day that way. But I have multiple copies of the data, and I have to manage folders within S3. So feature store is a nice way to actually add more metadata. So and have that metadata managed in something more than just the directory name where I'm storing these features. And so some of this still might not make sense. These start to get into the advanced use cases, more like sort of enterprise use cases. But then also keep in mind that there are typically many different machine learning tasks happening, and people like to reuse features. So think of a feature catalog or a feature hub, if you will. That's essentially what feature store is, where one team has already modeled me in my Netflix or in my Uber, and there could be some other like modeling tasks where people are trying to train models that want to get access to those features. And so feature store is a nice central place to put everything. There's two types of feature stores. There's actually online feature store, which is meant more for when the user logs in and sort of inference time and kind of real time. But there's also what's more commonly used, which is the batch offline feature store, which is where you would, as you're creating features, you would then put these features into the feature store to be shared everywhere. So here's an example. Here's a review of 5, and I needed antivirus and no equality, blah, blah, blah. That was apparently a good review. Here's a medium review, neutral review, and then here's a bad one, has the word terrible, things like that in it. So all we're doing here is just saving into the feature store. So let me just get to the good stuff here. This is feature definition. So this is what our feature store schema looks like. Again, seems pretty basic and seems like you can, do this in just CSVs on your like local laptop, but that doesn't really scale, and certainly not as collaborative as using something like feature store. So with feature store, you need to give it the unique ID for the feature. Here it's the review ID, pretty common to have unique ID, and also the time. And so we'll use date that review was provided. All right, and here we create it. We're actually turning on the online store. Yeah, Ansha, let's remember to flip that to false because we're only working on the offline one for the most part here. Describing it, so feature name, same thing that we just did here. We're gonna wait for it to create. So because this is creating tables in Dynamo and S3 and doing some fun stuff on the back end to tie everything together and set up all the permissions. We do have to wait, just a few seconds here for it to come back. And now we'll start to get to some of the BERT stuff. So let's get back into BERT. So max sequence length. Yes, if you recall, me and Ansha showed you in 03, which I still got to run here. Let me run it. And she showed you where we wanted to capture 80th percentile. And where'd the thing go? So 80th percentile of all of our reviews ends up being less than 64. And so again, we're choosing power of 2. So the number of words, or technically tokens, needs to be less than 64. And so some of you might be saying, well, wait a minute, each word can actually expand into multiple tokens. And here's one right here. So the word antivirus, which in the actual review up here was a full word, actually got split into, sorry for the scroll here, get back here. That word got split into 2 different words. So BERT had learned the word anti and had learned the word virus. And so when BERT parses the text into tokens, it's going to split those 2 words. And so this actually handles, by the way, the out of vocabulary scenario, where you may have a word that BERT has never seen before. BERT can split it into 2 different words that it does know, right? So this is very powerful. So this has been done before BERT and before transformers, but I just want to highlight it here that if you do have some word, BERT will try to break it down into more primitives that it has learned. So something like no brainer. So brain is a full word, and then it's doing pound when it has split the word, so that we can distinguish if it's a root, or if it was the first part of the word, or if it's been split. And then these are the actual input IDs. So 101 so this is a BERT specific implementation, but that's really the start of your sentence, and then SEP is the end of the sentence. And so if you see 101, that's always CLS, and BERT injects that in. This way we know where the sentence starts and ends. This helps us do 2 sequence type of natural language tasks. And sequence, basically just think of it as the sentence or as the document, or in our case, the review, which could be multiple sentences, by the way. It knows when it started and when it ended, and a second review. So if there are 2 things that always follow each other, like question answer, BERT can learn and will split those 2 sequences or sentences or documents using that the CLS and then SEP. So that's out of scope for here, but just know question answer tasks are handled by BERT, and yeah, actually work really well. But at the end of this, we convert text into these vectors. These vectors, this is a tiny bit more detail, but each of these actually goes into or expands into its own 768 vector embedding. So this is more of an index into another vector matrix. And at position 1045, for example, the word I has been represented by 768. Yes, I haven't gone into that too much. It's just too much detail for here, but just know that 768 is a key number, and some people will talk about that. So we chose 64 for the maximum sequence length. If you notice, so there's 64 here, but there's also a whole bunch of zeros, and that's because this review is less than 64. And so BERT pads with zeros. This is why I was saying, if you go to 128, you'll just have more zeros. And the way BERT has been implemented, it is going to represent this whole vector no matter what. It's an implementation detail. It seems like this could be optimized, or could use sparse instead of dense, and why are these zeros being treated this way? It's just how BERT works. Also note that 512 is the maximum for most BERT variants. There's a newer BERT variant that is going to be part of the next release of Hugging Face. This is something I'm going to ask the guy on Monday when he comes on to the webinar. That's called Big BERT. And Big BERT can actually go up much, much higher. It's a slightly different implementation that's meant for longer form documents and can do all the same things like text classification, can do question answer, all that stuff. It was a very common complaint that 512, which is the current maximum max sequence length, was not enough for certain use cases for larger documents. Yeah, however, 512, doesn't even really show up, I don't think, on our long tail here if we go to the bottom. Oop, this one didn't run yet. Anyway, yeah, so Ansha showed it to you. So, 128 really captures most everything. I think 256, does pretty well as well. Or sorry, captures everything. 64 works well for us. It trains quicker, uses less memory, and uses less compute. So we like 64. And here's just some of those other implementation details. Really, this is telling BERT when to stop paying attention. When does it actually end up being all zeros? Seems like it should be able to figure that out on its own, but just in case. Segment IDs, this is all zeros for us. If we were doing a two-sequence classification or a two-sequence natural language processing task like question and answer, these would typically flip 0 and 1. That means question answer 0 1 0 1 0 1. It's all zeros for us because we're doing a single sentence or a single sequence natural language processing task. Here's label ID. It was converted from 5 to 4. So this is the actual label. This is the label ID that's used for training. So this is what we're actually putting into our feature store. And we are also, by the way, not just putting into the feature store, but we are generating CSV files, like TF record files that will then be used by TensorFlow. I've seen some people put the actual TF record data into the feature store. I prefer to keep the TF record data on a file and then can be distributed nicely across our cluster, but I've seen people do it both ways. All right, and here's just some more examples. We see install got broken into three actually. So for some reason, and then keep in mind too, BERT has a vocabulary of 30,000 tokens, and this doesn't seem like a lot, but keep in mind that multiple tokens can make up one word. And so, maybe BERT didn't pick up the word install because it wasn't one of the more common words, or it just chose, but it has picked up fragments and can still represent this word, but actually this is uninstall is the full word, and then still model that out of vocabulary word or word that did not make the top 30,000 that the BERT vocabulary exposes. This is a typical warning here. 512 is the maximum for BERT. Again, if you use Big BERT, it can efficiently operate on larger than 512 sequences. If you want to know the details, which is actually pretty interesting, BERT is essentially, I believe, an n squared type of operation. Ultimately, ends up being n squared at some point, which doesn't scale past the 512. It becomes computationally infeasible. Whereas Big BERT actually gets that down to, I believe, n. So a little trick there for those of you preparing for your next interview and studying Big O. You can bust that out about BERT and Big BERT, and you will get the job. Okay, here's where we're actually putting in the data. This is the live feature store. If you wanted to, we could actually go to over here, which I think I have a screenshot later, but you can click over here and go to feature store. And you'll see I actually created a second one because I'm running a pipeline, but let's go into one of them. You'll see feature definitions, all the same things I was just talking about. I don't think you can actually query from this interface. I've asked for that, and I know customers Yeah, I've asked for it, but I'll show you here in a sec how to query it. We'll actually do it right from the code. All right, so we first need to get the data in. So you can give it a data frame, classic pandas data frame. You see some of the implementation details popping up here in the UI. Here we're using the real-time or the online feature store to get a specific record, and that's all the data coming back. So kind of useful. So I guess we don't actually show. Why are we not show? Oh, yeah, no. Oh wait, that's from Dick. Yeah, for some reason, yeah, Ansha, it looks like we're not querying the feature store, the offline feature store here for some reason. So we should add that. But it's basically a query, select star from this particular feature store name. In fact, I showed the query up here, and there's a way to execute queries. I think we actually have it in the pipeline section, right, Ansha, where we query the feature store?
We have to check. I think
Yeah.
we simplified a little bit of the code here.
Yeah, okay. All right, let's jump over to actually training. So spent quite a bit of time, about a half hour here on feature like transformations. We were doing it only in the notebook. This next notebook, we will only train within the notebook. And then 07, we will kick off training and do all of this automated as a complete pipeline. No notebook code involved. It's just going to be all, optimized Python code, or fairly optimized. It's not the best Python code, but it's at least readable, I think. So run 06 if you haven't already, kernel, restart, and run all. All right, so here's that same tokenizer. So when we're training, actually, yeah, how are we using tokenizer here? All right, that's just for a sample. That's just sample stuff. Yeah, we actually don't need the tokenizer, except for if we wanted to print stuff out. But the transformed features will come from the feature store or come from the TF record files. So the actual tokenizing has already been done. And let me just zoom in here and show. So I think I already talked about pre-training versus fine-tuning, but once again, BERT was pre-trained, which is an unsupervised task, by the way. There's supervised and like unsupervised. Pre-training means the like unsupervised part means I'm just going to give BERT when BERT was trained from scratch. BERT was just given a whole bunch of docs and told to make sense of it. It's doing two things. It's actually masking out words within a document and then trying to predict. So I believe it's masking 15% of the words. So it just keeps looking at this data over and over and over and trying to predict what is the missing word. And when you do that enough times, you start to be able to learn language. Seems super simple, but at scale, this works pretty well. Also, at the same time, it's doing next sentence prediction. And so I've hinted at this before with question answer, but the BERT model is learning what is the most likely next sentence, and is predicting, if given this sentence, what have you learned to be the most likely next combination of words? And so it's constantly doing this both at the same time during pre-training. This is all unsupervised. Now we actually have a data set that we want to perform supervised training, reusing all of that knowledge and specifically those weights that have been learned in that model, and now pass it through and learn our data set. Named entity recognition, probably one of the most common I've seen anyway in my days, like before AWS and then even at AWS. Yeah, of course, text classification, question answer, very, very popular. But the NER stuff, named entity recognition, comes in very, very handy, comes in for a lot of different types of use cases where we're trying to recognize within a sentence, is this a product name? And so at like Amazon, for example, we have a huge product catalog. And yes, I don't know this for sure because I don't work with that team, but my guess is they are able to look at a review or yes, anything, social media, anything, and pull out whether or not they're referring to a particular product in their product catalog. And then can, potentially learn sentiment, can learn, but that ability to pull out people, places, things, like Michelle Obama, for example, being able to see that word and know that that's a person, and then be able to figure out who that person is, who they are speaking about most likely. There's lots of use cases that find that useful. Okay, so this is what we're doing. We are not pre-training from scratch. In fact, there are very few times when you really need to pre-train from scratch. Yes, I say that depending on who you are. If you're LinkedIn or someone that works at like LinkedIn, you will be training or pre-training BERT from scratch because your domain of job listings, people, resumes, recommendations for people, right, like recruiters, all that stuff is very specific to LinkedIn's domain and does not necessarily match Wikipedia or Google Books. If you're right, like Amazon, for example, if you're Netflix, you have your product catalogs or your domain specific features that you may potentially pre-train BERT. And I pretty much guarantee all of those companies are pre-training BERT. Typically how it works is they try the base BERT just to see how it works, to see if they can avoid pre-training, but they very quickly realize that they do need to pre-train, which goes through all the unsupervised, does the next sentence prediction, does the masked, masked word task, and then ends up with a pre-trained model. I just showed you feature engineering, which is that the middle part there. And now we're going to do the actual fine tuning. And really all we're doing, again, to like Andrew Ng's point, all of these algorithms are totally usable. All we need is good data and clean data, which is, one of the harder things. So all we're doing here is adding a simple classification layer on top of the pre-trained BERT model. So BERT will be one layer within our TensorFlow, Keras model. And it's a very thick layer, 66 million parameters for distill BERT. But all we have to do is just add simple, let's see, I think, yes, I'll show it here in a bit. But we have, yes, obviously softmax layer on top to get the final star rating, but very, very thin. I think we're using Atom Optimizer. Yes, I'll show it here in a bit. And so we didn't have to do all that pre-training, but we still get a very, very powerful text classifier using our specific data. We train it with the review body and the star rating. That's all we're going to do today is just use review body and star rating. You can certainly use product category. You could use, if you want to join with the pricing catalog or, pricing sheets, like data set, which I don't think is public, or it was public at some point and then it's not public anymore or something. But there are many other features that you should use when you're doing your modeling. Today, we're just sticking with the text part. It's the most complicated, most interesting, and the one that we will show how to solve. All right, so this is it right here, TF distill BERT for sequence classification. The Hugging Face folks have implemented this. There's PyTorch version as well. And this is specifically for sequence or like text classification. There's also a transformer implementation for question answer. There's also named entity recognition. And the cool thing about this workshop is all you have to do is make a few changes, put in your data set, which isn't super easy, but you just take our code, you can modify and change it to your column names and change this to be whatever task that you're trying to do. If you're trying to do named entity recognition, switch this out, and pretty much all the plumbing is here for you. And now we have to decode the actual TF record to make it usable. And so we have to give TensorFlow a hint as to how to map what's in this unreadable binary format into something readable. And so TensorFlow is fully optimized for this. I'll, just tell it how to make the mapping, it's going to do it. Here, we're telling TensorFlow to shuffle the data. So this is important for most use cases, time series excluded. You want to shuffle the data. And so what happens is if you don't shuffle your data during training, your model will potentially learn the order in which that data is being presented into the model. So, and we are typically going over multiple times this data set, multiple times. They're called epochs, E-P-O-C-H-S. Yes, epochs, some people say. And if we don't shuffle, we are always going to see the data in the same order, and the model may actually start to learn that order and make predictions based on the order, which is not what you want typically. With time series, yes, very important. Most other use cases you want to shuffle. All right, here so this is just sample TF records that were created offline. This is just to get through the notebook. We will wire all this up in the next step during the pipeline phase. Max sequence length is 64. Oh, by the way, yes, I didn't mention this, but we did feature engineering with 64, if you recall, for max sequence length. If you wanted to try 128, you actually have to go back to the feature engineering step and change that to be max sequence length 128. You can't train on 128 or 256 if your data was transformed using 64, because again, those buffers are 64 numbers long, right? 64 bytes. So let's see. Apologize. So this is very important. This is a hyperparameter that you will definitely want to tune specific. Yes, like I said, me and Antra chose 128 because that's what a lot of the samples we were looking at were using. And so we didn't have any other reason to try something different. So we started with 128, but we were using pretty big instances and we're trying to reduce costs, but keep the accuracy pretty good. So we looked at our data set. We saw that chart that said this, 80% seems pretty good to us. If we can capture that, let me get to the bottom of this. This is really annoying, I know. I just want to tie all this together. So there's 64. So the 80th percentile is under 64, which is good. If we wanted to capture 90%, we'd have to bump to 128. But we still see pretty good results and less memory. But just know that if you do want to try 128, you have to re-engineer your features. And so this is where Feature Store comes in handy too, because I can actually populate my Feature Store with both the 64 version, the 128, and the 256. Or if I think I'm going to be using Big Bird at some point, then yeah, I might as well go ahead and then transform these features. One big job for both 64, 128, 256, 512, 1024, 4096, yeah, all that. So, and then when you go to train, all you do is point to the Feature Store with the value that you are currently using, max sequence length that you want to use. Okay, so hopefully that makes sense. It's a special hyperparameter in that it actually requires new features. Most hyperparameter tuning, we just change, things about the numerical optimizer, like the learning rate for gradient descent. Yes, epsilon for the atom optimizer. But this is a hyperparameter that cannot be tuned easily, not without actually backing up into the pipeline and re-engineering your features. So fortunately, we're sticking with 64 everywhere. Number of the epochs, because we're doing this in the notebook and we don't have a whole lot of resources, we set this to 1. When we do the pipeline, we'll actually bump this up to higher. Steps per epoch, let's see. So steps are the number of, I guess chunks, yes, if you will, that we will go in through per epoch. So here, I'm just setting everything to be 1. Freezing the BERT layer. So while we're doing this fine tuning, this is a pretty advanced topic, but actually this came up on Ansha's interview from like what I remember from her like AWS interview was about freezing. And what does that do? What are the implications? So it's a fun topic, you know, fun when we start to go back to in-person parties, you can impress your friends and family. When you freeze a layer, you are not letting those weights change during training. And so we are training, it's technically fine tuning, but we're training a classifier. And there may be, for like whatever reason, maybe we only want to focus on our classifier and not actually retrain what BERT has already learned. In most cases, you want to unfreeze BERT. You will typically get better accuracy when you let the whole network be, you know, back propagated and then updated. But you will definitely train faster if you don't, or if you freeze. But you may get lower accuracy if you freeze. Because we are in the notebook, I'm setting it to be the least accurate and just don't crash my notebook server setting, which is freezing that BERT layer. So my classifier will still learn, but my BERT layer stays fixed. And there's lots of systems implications here and systems optimizations. If you have a value that cannot change, there are certain parts of the runtime that get optimized. This is the immutable. If you're, you know, functional programmer, Scala programmer, something like that, where you've dealt with immutable values, there are huge systems optimizations that happen at the runtime layer because you physically cannot do an update or, you know, adding or something, or like deleting. It is a fixed value that can never change and therefore can be optimized by the runtime. So my suggestion is to try it frozen because you'll train quicker and cost less, but typically you will want to unfreeze. So yeah, try explaining that at your next dinner party. It's like not that easy to explain, but if like you have a whiteboard, maybe you can bring a whiteboard and you could try to whiteboard it out. All right, Distilbert config. This is pretty cool because I can actually change the meaning of what 0 means. So here I happen to be using, you know, 1, 2, 3, 4, and 5, but I can actually change this to say star rating 1 and, you know, give it strings. And so other people that are reusing my model, my fine-tuned model, can actually modify what comes out of those predictions. So 0 is the same, it's 0, 1, and 2, but, you know, this is a dictionary. So I can make this, you know, whatever, you know, bad, and change this to be not so bad, right? So I can change how, not what BERT is doing on the inside, but I could change what's actually coming out. And same with going in as well too. So this would be, you know, star rating 1 ends up as the 0 index on the inside. So it gives you a little flexibility. I show it, it's probably too much detail. You don't even have to like override these. It'll make some intelligent defaults. Here's that vocabulary size, by the way. So this config will be different based on which variant. So this is model type Distilbert. This has vocabulary 30,000. If you use Big Bird, this will be much higher. Actually, the vocabulary might be the same, but it can just handle larger sequence lengths. Here's that 768 magic number that I said. So each token, although it seems like it's just one number, 101, each token is actually its own 768 vector. Okay, and this is that Distilbert for mask. This was the masking 15%. All right, so this is really all that you would need to write. Now, we've done a few optimizations here, yes, empirically. Here we're, let me zoom out a little bit, give some more space. So this is the whole heart of today's workshop and creating our classifier, fine-tuning BERT. So the very first layer of our model is going to be Distilbert. And before this existed within transformers, this was a massive amount of code. And in fact, when Ansha and I first started writing the book, we were using that massive code. Transformers and like Hugging Face only supported PyTorch, and me and Ansha chose TensorFlow for the book. We do have lots of like PyTorch examples. We have a couple MXNet examples as well. Yeah, we even have Java examples that are doing BERT. But this really takes care of a whole lot of code. This sets up BERT to be fine-tuned. And then we are passing in the input IDs, the input mask. So this is our very first layer. We're then adding just a simple bidirectional LSTM. This is just kind of helping out with that final layer. But we've seen people do something as simple as just one layer here and then adding dense, dropout, and then dense again. I've even seen people just use BERT and then a single dense, which really isn't training that much. So here we're just giving more dimensions, if you will, or more opportunities for BERT for our classifier to be trained. Okay. We give it the final number of classes, which is 5, 1, 2, 3, 4, 5. We tell it to use softmax because this is multi-class classification. And then everything comes together here. We're choosing to freeze or not freeze. This is just the goofy way. Well, actually, this is more readable than the way PyTorch does it, but you say trainable equals true or false. And for about 2 months, I had this wrong. I forgot the not. And so I couldn't figure out why I was getting bad accuracy, or actually good accuracy for this case. Okay, and then this is where everything comes together, where we set up the cross entropy. So sparse categorical cross entropy, that's our loss function. We are trying to optimize for the like accuracy. We set up the optimizer, numerical optimizer, give it the hyperparameters, and then call compile, pass everything in, call model summary, and this is it. We have 2 of these inputs. We have the base BERT layer, which again is 66 million parameters that have been trained. We have 64 tokens coming in. Again, each token is 768 in length vector. And then we have a couple extra parameters here, 300,000 for our bidirectional LSTM, 5,050 for one of the dense. For a 50 dense layer, we add some dropout. And then final layer is this dense layer of 5, which is 1, 2, 3, 4, or 5. We will actually then see what is the highest value that comes out of this, because this is a like distribution. All 5 values will be populated, and we have to then do softmax and like argmax to actually get the true prediction based on the confidence. All right, and here we see trainable versus non-trainable. So the frozen parameters are BERT. The trainable are all of the layers on top of BERT that we've added to our specific fine tuning. We could use TensorBoard here, and this is where we actually call fit. Now this accuracy looks terrible, and that's because we only do 1 epoch for 1 step. And we see, let's see, training accuracy 25%, which is pretty bad. Validation accuracy is pretty much 0. Don't worry too much about that. This is just showing what is actually happening inside of our pipeline. I want to point out a pretty slick, if you are using TensorFlow, so we do plan to serve this model as an endpoint, a REST endpoint. And in doing that, we want to save our model in a format that TensorFlow serving can serve up. So TensorFlow serving was actually a very early part of TensorFlow. So first TensorFlow core came out, then TensorFlow serving came out, and then TensorFlow distributed came out. And so TensorFlow serving has been there from the very, very early days. Google uses TensorFlow serving for quite a lot of stuff internally. And one of the coolest, most hidden or non-obvious features is this way to print the signature of your model as it is seen by the outside world. And so no surprise, it's taking in input IDs and then input mask, right? It's not taking the raw text because the assumption here is that the text is being tokenized somewhere else. And so we'll tie all this together when we show pipeline. But we have the input IDs and the input mask, which is actually using the exact same tokenizer that we used in the previous notebook. And then out comes, no surprise, a distribution between 1 and 5, this dense layer, at which time we'll do the softmax and then grab the star rating. Okay, and just to test it, we will actually do a sample prediction. Oh, and so this is called saved model CLI. There's also a Python API that's been added where you can call it from Python, but this is the actual. When you pip install TensorFlow, save model CLI gets installed. Okay, and here we're going to simulate as though we're making a prediction. So we're going to load the model from that saved model directory that we just looked at. By the way, I find this very, very useful, especially when I'm modifying the model and trying to make optimizations. Oftentimes I'll screw up either this last layer and I'll suddenly see 5050, or I'll screw up the inputs and suddenly see only 1 input or 5 inputs. And that's a clear clue up front when you should step back and not deploy it. Like typically I would have deployed the model, found out after going through all this these motions to actually get it approved and then push it out, to find out that the signature is not the right signature, and then I have to go back and retrain the model. So this is simulating. So this is what's going to get done outside of the actual prediction. We'll show you a Python script that gets injected into SageMaker Endpoint that will basically do this exact code. Grabs the input IDs, grabs the input mask, also called the attention mask, calls predict, grabs the label, and we actually, let's see, yep, there's our star rating here. So this is a very, very bad model. It's pretty much, although it seems to match up here, but star rating 5 for this product is great. That's probably just a lucky choice since this is only 25% accurate. Okay, yeah, any questions, Ancha?
Yeah, a lot of questions actually coming in around the BERT and feature engineering. I think a few questions I kept for you here. People were asking, I think you initially, when you started with the feature engineering, you mentioned some good books, resources people could maybe read to read about feature engineering. And then questions came also up for if we know of good resources for different use cases apart from NLP, where to find them. And you're muted right now. I think I don't know if you're explaining what you're searching, but I see you're looking for the books here.
Yeah, yeah, I was talking a lot there. There's quite a lot of examples. So SageMaker examples is a really good place to go. Let me paste this in. And let's see, SageMaker examples is good for XGBoost examples, which is very general, can pretty much do like everything, classification or regression. There's lots of computer vision samples as well. We actually thought about using computer vision for the book because there were so many resources, but we felt there was kind of a plateau or there's just a saturation of computer vision examples. We wanted to be a little bit progressive and skate where the hockey puck is moving, as I always say. So we chose NLP, and yeah, Hugging Face came along at the right time and really implemented all the stuff we were trying to implement.
Yeah, and can you put in the book? Yeah, perfect.
Yeah, and funny story about Amanda. I actually met her up in Seattle. She and I were in a training course together, and of course it's Seattle and it rains 23 hours out of every day. She actually gave me a ride back to my hotel. which is very nice. And then we've stayed in touch, and yeah, really good book. A bit of an older one, 2018, and that's kind of the secret to feature engineering is things don't really change. You know, models changing all the time, but that's on the research side. On the data side, data doesn't really change. Like data is pretty much the same. There's, you know, categorical, tabular data. Yeah, there's obviously NLP data, image data. So I think this is more on the categorical. Let's see, this is, yeah, bag of words, engrams. There's another one. There's a packed book that I like, feature engineering. Python feature engineering cookbook that I just started reading. This is a pretty cheap one. It's probably more similar to, because I think this is a little bit older as well too, but if you're like me, you want to continue studying all of the fundamentals because pretty much everything builds on that. Okay. Yeah, if you're
Yeah, a lot of
so
yeah, a lot of questions around comprehend services, how to use named entity recognition, for example, instead of text classification, how to do multi-label. So I've shared a couple of links here. We actually do have one sample notebook in the workshop that shows a named entity recognition. It's not included in the full pipeline we're running today, but if you're just looking for some code, how to do that. And I've also shared a link to the Hugging Face repo, so they're also having extensive documentation for the different NLP tasks. So if you're just looking for maybe how to adopt that, samples that we're doing for the classification, maybe to a Hugging Face entity recognition, that's also a good start to look for code samples. Okay,
so one person stuck at the 91%. My guess here is to kill all the kernels. I would kill all your kernels. So just in case anyone's, so quick, if you click on this little square in the circle thing, you can actually go here and shut down all the other kernels. Sometimes we see people run out of memory if they've run a whole bunch of stuff or gotten very exploratory and poked around. Kill all of these and try to rerun it. But at this point, Ancha, I think we should switch over to 07, right? And run the pipeline?
Yes, and I already told people to start it. So if you haven't started CR7, please do so. The pipeline will run for approximately 35 to sometimes 40 minutes. So please make sure to start running it.
Yeah, and just to keep you, so this ran for 38 minutes, just to kind of whet your appetite a bit. This is what you'll end up with over here. I'm zoomed in way too much. You will end up with this pipeline, and you can click on each of these nodes in this pipeline. And if you've done anything like Airflow or Kubeflow, things like that, very similar API where you're wiring up a DAG. And we'll show this after the break, but yeah, let this run. We'll come back. Some of you probably it won't be done yet, but you can follow along and yours will finish eventually. And then after that, we'll show how to evaluate the model. I should probably run mine right now. And I do want to reemphasize, because I noticed some of these questions in the Slack, that some of you might be wondering, why are we writing all this code? Like, why can't I just go into my like local laptop or my development server and run some Python notebooks and then call it a day, go home? That is more ad hoc analysis. And yes, you can train, and you probably have gotten very, very far in your current environment. And some of this won't make sense. When I got to Netflix, I thought people were crazy. I was like, why are you doing all this stuff? Why are you running Hive queries? Why don't you just query your relational database? And people laughed at me, right? So I was new to the Bay Area. I didn't have a whole lot of scale experience. And so sometimes I speak from all that experience and don't always like emphasize this, but if this doesn't make sense to you, that's okay. Just know that when you get to a certain point with your current job or maybe your next job, where you have much more scale, this stuff makes sense because traditional database queries don't you know, I can't query my Netflix, you know, 100 million subscriber catalog to, or yeah, so that one's actually probably okay. But when you start to query log files coming from 5,000 streaming servers that are operating 24 hours a day and trying to find one needle in this error message haystack, this is near impossible with a traditional database. And so similarly, if I'm training with 150 million, or sorry, 100 million subscribers, and there's a product catalog of 150,000 movies or 500,000 movies and TV shows, these things do not run on a single database or even a Oracle federated database. This is big time stuff that has to happen in a MapReduce kind of way. So Spark is still MapReduced, right? Like a lot of people don't know that, or don't think about it that way. But when you're running Spark jobs, you're doing MapReduce beneath the covers. It's just easier than writing, MapReduce by hand. Yeah. So anything else, Ancha, or should we take a break? We'll go to
let's take a break. Yeah, and maybe you can scroll through some of the questions. You might want to add something. Yeah, shall we do 10 minutes?
Yeah, we could do 10. Most people's stuff won't be done, but we need to get through, right? We're doing 8 to, oh.
Well,
yeah,
and we're walking through the notebook. So while we're explaining it. Yep, okay, let's do 10 minutes. So we have a chance to get through.
Sounds good. I thought we had 1 more hour. I was babbling there, telling stories.
Yeah, I should never tell you we're good in time when I hand over to you. That's my mistake. No, we're good. All right, shall we resume? How's everyone doing?
Yeah, I didn't get a chance to answer too many questions. I had to get some more coffee here. Okay. So good, it looks like people got through all 12, so that's fun. You don't need to run 12, by the way, cleanup, if you want to keep experimenting. We tear down these accounts anyway. Cleanup is good for when you are doing it on your own. You want to tear down all the resources that you started up. Okay, so I'm doing pipelines, right, Ancha?
Yes, why don't you do a quick run through pipelines?
Yeah, because we only have 30
And
minutes.
maybe,
Okay.
yeah, maybe you can focus on 10 minutes and then I can take the rest.
Yeah. So the good news is we've pretty much already explained to you everything that a pipeline is doing. There's some new concepts here. Someone asked about Kubeflow. Kubeflow, Airflow, and SageMaker Pipelines all logically do similar things, similar to Spark, actually, where, well, yeah, let's keep Spark out of this, but the graph of like execution, right? So commonly called a DAG, directed acyclic graph, DAG. Any kind of pipeline, if using Jenkins, yes, I mentioned Spark because Spark actually creates a DAG of transformation steps, you know, and so DAGs, what we're doing is basically wiring up all the steps that we had previously explained, where we're, you know, first checking for, well, yeah, so let's just like walk through these. We're going to create a pipeline. Pipeline consists of different steps. The types of steps that we're going to use are processing job steps. This is what we're going to do to transform our data. So what we did in 05 will end up going into a processing job. What we did in 06 will go into a training job. When the training job trains a model, we will conditionally check the accuracy of that model and register the model and deploy it if the accuracy is above a given threshold. So if we get better than 20% accuracy, for example, we have 5-star ratings, 5 categories. If we get above 20%, which is random chance, we might want to deploy it. If we get up to 70 and then we do another training run, we might not want to deploy the next model until it's at, you know, higher than 70. You have control over when the model gets deployed. When we register the model, we assign it a status of either pending approval or approved for staging, approved for production. We will also show lineage too. That's not really mentioned here, but each of these steps has clear inputs, outputs. Also, which you know, which version of PyTorch or sorry, TensorFlow, which version of Scikit-Learn, all that stuff is being tracked. We could also do batch transformations, which is batch predictions, which we're not doing today. We're actually deploying an endpoint. So if your thing has run, click over here on pipeline, double click on pipeline, and let's work backwards from here. So this is the whole pipeline. I can actually schedule to run a new execution. I think back here I can actually do start an execution, and I can give it a new name. Now we don't have to do this here because we're already doing it programmatically, but this is the superset of all parameters that are used across all steps. And so, you know, when Ancha and I were actually lowering from 128 to 64, this is what we did. We actually came in here, changed this to be 128, ran the entire pipeline, which does the feature engineering at the 128, which is, you know, once again, that special hyperparameter that extends previous into, or extends earlier into your pipeline during feature engineering. Something like that. And so here we can see all the parameters, whether or not we're going to balance, not balance, max sequence length, all the way to the epochs, number of epochs, and all that. Okay, so let's go back here. This is what it looks like. Bunch of boilerplate to set up and get ready to use our SageMaker SDKs and Python SDKs. Here's where we're actually copying the data. Someone was asking earlier, where do we actually copy the public data to our private bucket? And this is where we're doing it as part of the pipeline. We've chosen to only do 3. We typically do all the data, but we wanted to keep the training time down today and keep the accuracy fairly high. So we choose 3 of the, I think, 43 or 45 product categories. Here we've got some boilerplate in here. This keeps, when people do run all, if they get frustrated, like they think there's an error with the notebook because it's taking 38 minutes. We've noticed people going up here and trying to rerun, and this prevents bad stuff from happening when people do that. So a lot of this is just boilerplate, kind of workshop at scale, best practices here. But just note, so similar to Airflow, similar to Kubeflow, when we're defining our graph, we have to provide placeholders. Either strings or integers or floats are the 3 most common. So, and these placeholders can be hyperparameters, they can be, whatever. And that's exactly what we're using them for today here. So we are using that same diagram from before, where we're using a processing job, Scikit-Learn, TensorFlow, and then also Hugging Face. So this is setting up the processing step. Here's where we set up the names of these placeholders. So again, there's no value. We do have a default value. That's a nice little feature, but we can override these values when we actually run the pipeline. So here I'm just setting up placeholders. And I can print this variable and it'll show up just like a Python variable, but really it's the parameter string construct in the back, which is a very common pattern for all these workflow engines. Also, one of the other benefits to using SageMaker Pipelines, just in case you're thinking, why would I ever use this when I'm currently using Airflow or Kubeflow? When you have SageMaker Pipelines, you are automatically doing all the lineage tracking. The experiment tracking is all integrated. So you don't have to write separate code to do MLflow, to be writing to an MLflow server, and then you have to manage that MLflow server. All this is just built in for you. Yeah, and there are and so the other cool feature about pipelines is you could do step caching. So each of these nodes in the pipeline is a step. And let's say, for example, I want to rerun with some different training hyperparameters. Let's say I want to try a different learning rate for my stochastic gradient descent optimizer, ATOM optimizer. I can rerun this pipeline, turn on step caching for processing. And if I've already processed, the data hasn't changed, then SageMaker Pipelines knows that the output hasn't changed. It's just going to skip that whole first 5-10 minutes and just go right to the training. So step caching, very powerful, very common in other things. Even Jenkins, all that stuff can cache steps. Here we're setting up all the same inputs and output. So we've got the raw data set. These are the tar GZs. And I know I'm out of time here. Processing outputs, the 3 different output locations. So we're splitting the data into train, validation, and test. I didn't cover that in the feature engineering 05 notebook, but just know that we're taking 90% of our data of those reviews, using it for training, and then 5% for validation and 5% for test. Seems to work okay for us. Because we are using hyperparameters, we may want to try different hyperparameters, so that's why we have a validation. And then ultimately, we are testing the combination of hyperparameters with our third data set called test. So here, we're setting up the processing step, passing in the split, the max sequence length, if we're going to balance or not, passing in the feature store information, so we could store the data in the feature store. And then a bunch of hyperparameters for training. I'm going to skip over these because we've seen a lot of these already, like epsilon, learning rates, freeze BERT layer. So by default, it's false. And then, but yeah, once again, when we go to actually run the pipeline, it will use the values that we give it at that time. These are just defaults. I'm personally not a big fan of defaults because they have always burned me in the past. They've never actually added value, and they can only like remove value basically. So never use defaults, but we show them here anyway. And training and validation. So here's where we can actually convert a print statement inside of our train.py. So one thing I've been not very good about showing you is the actual source files here. So tf-BERT reviews, this is our train.py basically. And this thing, either from TensorFlow or from us, is writing things to the console. We can scrape those logs, convert them into metrics that then show up in CloudWatch, or we can push to Prometheus, or we can push anywhere. So we have the accuracy, we have training accuracy, validation accuracy, training loss, validation loss. We will talk about inference.py. I'm just going to talk more about inference.py, but train.py or tf-BERT reviews.py is what's actually running here. We've got debugger turned on here as well too. We can get notified. I can actually get paged, like a text message. Yeah, I'm not going to get paged. And if my job has plateaued, if I'm not making progress, I can set up all kinds of rules with debugger. Yeah, Ansha knows this stuff really, like super well. She wrote this part of the book actually. We can then look at a live report will get generated. So here is where we're actually doing the training. We're passing in all the profiler configuration, debugger. So we will profile CPU, will profile IO, and we will present to you a full report that says you should actually be using a smaller instance because you're not fully utilizing it, or we'll say bump up your number of epochs, bump up the batch size. But that's one of my favorite things about this is that SageMaker will actually tell me when I'm not fully utilizing and actually suggest that I use cheaper instances, which is, earns a lot of trust with me. Training. So note that we're passing in placeholders here. So again, all we're doing at this point, I'm not executing anything just yet. So I won't actually start the pipeline until the bottom, but here I'm just wiring up the inputs from the output from the previous processing step, which is transforming our data into TF record, and I'm passing it as an input to my training step. So these are all just placeholders to say when you get to this point, use the processing steps output, these three for the different splits, and pass them in as input. Here's the processing, or no, this is the evaluation step here. So once the model is trained, we're going to run the evaluation. That's actually its own .py file as well, shows up down here. This is doing confusion matrix and then printing it out so we can pull in that confusion matrix later. This is also how we can get the final accuracy and then choose to conditionally register. So I'm going to first show the leaves of this tree or this graph of execution, and then I'll show the parent or the root. So I'm going to set up as though this is going to be like registered and then deployed, but then I'll back up and show how we conditionally determine if we should do that. So here, pending manual approval, I don't want anything to go out that does not go through me first. Deploy instance type. That's the instance type that we're going to use there. And here we're just wiring up more steps. So we're not going to register until the condition. So let me just jump right here. This is a bit confusing unless I show this condition here. So here's the condition. If my model is better than, okay, so this is only 1% accuracy. We could probably change that to maybe 20% to be, random chance for 5 labels for 5 categories. If it's higher than a particular accuracy, then run the register and then create the endpoint step. So if it's successful, if it's not, if it is worse than 1%, which is pretty rare, it will fail the pipe or just end the pipeline. It's not a failure necessarily. It's just not going to continue with deploying the model. All right, this is where we actually create the Python pipeline object using the SageMaker SDK. And this is where we actually launch and start the pipeline with all these hyperparameters being used. So this is where we can override. Wait for it to complete, runs for about 38 minutes, it looks like. Everyone's coming in around 38, I think. Now, this is where we're gonna list all the steps. So this is, pretty ugly JSON, not very usable. Let's take a look at a more usable way. So this is in my data frame, I can actually see all of my steps. So this is the transformation. So this is converting raw text into BERT vectors. We see the input was the S3 bucket, which Python file was used for that. This is very similar to our O5 notebook. It's not exactly the O5 notebook. It's been tuned for cluster, but all the code's there. You can take a look at it. The output is the 3 splits within S3. Now we go to the training. We see the inputs to training are the 3 splits from S3, and also which Docker image was used. This is a built-in image. It's all like open source TensorFlow. It's just optimized to talk to S3 and other parts of the Amazon, the AWS data science stack. And the output is this model tar GZ from our trained model, which is good. That's what we expect. This actually has our saved model. We can run save model CLI to look at the signature for that. Now we're going to do the evaluation. This is going to do the confusion matrix. This is going to output and give us a JSON file, which we will use to then determine if we should continue and deploy it. Next is where we actually register the model with a particular status. We can register the model with the approved status, and then it will be ready to be approved. We don't want to do that because we don't want to just be pushing out models, right, like without actually putting them into some staging area or otherwise confirming. I mean, some people do. That's the continuous deployment for your machine learning. And then here's a little bit of boilerplate. Let's look at the profile report. So at around cell 62 or so, you'll see a link. This looks empty, which is kind of boring. Click on this trust HTML thing up here. There's probably gonna be a lot of questions about this. So keep an eye out for this. Click on this trust. This should say distrust, and then you'll start seeing data. Click the refresh maybe. Okay, so here's how much time was spent in different areas. Here's how much CPU, IO happening. So this is really cool because I can see for a particular job, where is time being spent versus having to go to CloudWatch separately and other things. And I could see, here's my favorite suggestion. So here's CPU bottleneck, here's batch size. The batch size is too small. Consider running on a smaller instance or increase the batch size. So there's specific parameters here that say if it's not, and here's our P95 numbers and some other suggestions. Pretty cool. Okay, so I think that's it, Ansha. And then if you want to see it visually, go over here and click on pipelines. Yeah, do you want to take over?
I'll take over. That was a fast trek through the pipelines. I was just making sure that my notebooks here finished as well. So let me flip over the screen share. And here we go. All right, so Chris walked you through this pipelines, and there were a couple of questions how pipelines differs from the projects, etc. So I think I put a good feedback there. So SageMaker Pipelines helps you to orchestrate those individual steps, as Chris just showed you, right, from the pre-processing, the model training, you can register, etc. And also, if you want to explore, I'm not sure, Chris, if you had time to show this, in the studio environment, you can click on this down left menu item here in Jupyter Lab, and then select pipelines from the drop down, and there should be your pipeline. So you could have a look at this one to see if it succeeded or if it's still running. If you double click into here, you can see the graph of the execution of the individual run. And if it's completing, it should hopefully all be turning green and look like this. And you can also check the individual steps if you go to the console and check the training jobs, processing jobs, etc. All right, so we have roughly 10 minutes left. And I want to quickly show you here the remaining notebooks. So when 7 is completed, you can run 8, 9, 10, 11 in parallel. It's just showing a couple of different additional features here. So I've executed them so I can show you, and if yours are still running, don't worry, just watch, and we'll keep up the demo accounts for 1 more hour after this workshop so you can finish all the notebooks and see the results as well. All right, so let's have a look at 08. It's checking on the evaluation results. So if you remember, one step in this pipeline was to check the model evaluation. So what I'm doing here, again, just the usual code, and then I'm checking here that the pipeline has actually finished. So if yours finished, that should show here the succeeded. Otherwise, it doesn't make much sense to evaluate. I'm also listing the steps again, just because I can. But the more interesting part here is then look for this evaluate model step that we executed. And this one is run as a processing job. So I'm grabbing this here from the API response calls. And what I want to find here is where the metrics are stored. So this is the S3 output location. And then the step will write an evaluation JSON file, which I'm just reading in here. And this one contains the actual accuracy. And this is done by the code that got executed. So if you have a different use case and you want to calculate different things, maybe not the accuracy, maybe an F1 score, etc., you would just change that code that gets executed as part of the evaluation step. In our case, we calculated the accuracy. And you can see here, it's not too good. I know it's a 0.33, but we try to keep it very short in the model training. So we only ran training, I think, for maybe 15, 18 minutes. Otherwise, we would still be waiting on the pipeline to finish. So with those restraints and the small data set, it's good enough. You can bump up this number up to, I think we went up to 97% accuracy with much more data and longer training times. So that's definitely possible for the workshop. And getting us all back to our Saturdays, we kind of limited here training execution times. All right, what we also did, we calculated the confusion metrics, and we printed the result here as a PNG file. And this is also what we're just visualizing here. All right, and you can do anything really with those training jobs and the trained models. So here we're showing you also we're querying for the training job. And we can also download the model if you like. That's what we're doing here. You can have a look at the model tar. You can untar it, have a look. And this is the TensorFlow model that we saved and the Hugging Face Transformer model that we also stored in here. It's listing the individual artifacts again. I think this is what Chris showed in the pipelines notebook. So you can nicely see here in which step, which inputs contributed to the output, which is really nice. So for example, we see in the training step here, the dataset, the training dataset was the input, and the TensorFlow image that SageMaker used, and the output was the actual model artifact. So this is really a nice way to keep the artifact lineage across all of the steps here of your model experiments. All right, this was a short 08 that shouldn't take too long if you run it. And then a little bit more interesting, 0, 9, and 10. I promised you that we come back to SageMaker Clarify, and we're doing it right here. So in these notebooks in 9 and 10, we're using the same SageMaker Clarify library to now analyze our trained model and see if there's any imbalances in how the model runs predictions. And again, I know the topic covers probably a full day, but I do have a couple of links in here that you can follow up in the notebook. Again, the terminology of the bias metrics and the facets is the same, but we're doing now some post-training bias analysis. And here it's a couple of different metrics we can calculate. And you can see here the link that I put in to the documentation, which goes into great detail of how the individual metrics are being calculated. So starting from the difference in positive proportions in predicted labels to a disparate impact. So you can see all of the description and how to interpret them in the documentation. All right, so how to run this now on the trained model? Well, same setup code. And if you remember how we set up Clarify, it's pretty similar. So we need some testing data. And here I'm just using JSON lines as input data. This is how we specified the model to accept the inputs and also return the outputs. It's just yet another file format. So in here, it's a JSON line. And for example, here we're passing the features, and this is a review text, and it's labeled. So it has a star rating of 4, label training data sample. I'm uploading my training data here to an S3 bucket, and then I'm specifying Clarify. I'm just going through those pipeline steps. I'm just checking that the pipeline has completed again and that we do have a trained model. And what I'm doing here, I'm checking for the pipeline model name that got registered. And I'm specifying again my SageMaker Clarify processor. I'm specifying the instance types. The difference here is really that we're adding next to the data config that we already seen before, we add a model config now. And in the model config, I'm specifying this trained model that is the output of my pipeline. Could also be just a standalone trained model that you did. And also I'm giving it a definition of which instance and count to host it. So what Clarify will do, it will spin up this model that you pointed to on an instance so it can serve predictions. And then it will send your test data that you provisioned here in this data config to the model and see how it predicts. And then the bias config will analyze how the predictions behave against those bias metrics that it calculates, right? So all the code is in here. You can see how it's done. Again, we're specifying here a different file format. We're using JSON lines as content and accept type. And we're also giving it here a definition of the predicted label config. And this one is telling Clarify how to parse the prediction result out of the model response. And in this case here, it's a JSON field called predicted label. All right, and then we can do the same thing. We run in this case, post-training bias. If you remember, in the earlier notebook, we called run pre-training. Now it's post-training, passing the data config, the bias config. And the difference now is the model config. And we do have different methods, different bias metrics to calculate in this step. But in the backend, it's the same thing. It starts SageMaker Processing Jobs. It executes Clarify on the input data and using the pre-trained model. And you can check on the processing jobs if you click on those deep links again, and they take you right to the AWS console here and show you how the job is performing. So those jobs run for a little bit longer than the data bias because they will need to spin up a model endpoint and to host your model and run predictions. So those take roughly 12, 14 minutes each. And I'll show you the results in here. I think that's kind of the interesting part. So I'm scrolling down here and let's have a look at the bias report. So similar to the data bias, this will give you a post-training bias report calculating the new metrics, the specific metrics to check on the prediction behavior. And you will see that most of them will have a certain value larger to 1, larger to -1 again. A 0 would be, again, pretty much a kind of a balanced prediction behavior. Again, to interpret those different metrics, please check the documentation. And what you would want to do is, given your use case and the data, it's probably that you define a baseline where you say, okay, those values are acceptable. It's not as easy as with a data set where you can just, balance across number of samples in this case, because predictions are kind of depending on a lot of things. But you would define a baseline which is acceptable for those values, and then you would monitor the deployed model and trigger an alarm if you see that the model behaves outside of those accepted baseline values. And then you would have to look into it, probably retrain the model, etc. but it gives you a good indication of how your model is performing. All right, so this is checking for the model predictions. And if you run 010, that notebook is also using Clarify. In this case, it's using SHAP. If you're familiar with model explainability algorithms, SHAP is a pretty popular one. And the SHAP algorithm tries to identify which input features contribute to the final decision. And again, the setup is pretty similar using Clarify. Scrolling down to the interesting part. In here, again, the processor that we define, the data config that we define, the model that is used to run the predictions. And in here, we're just adding another item, which is the SHAP config. And we need to give it a baseline. And this is really just a sample of your training data, for example, without the label. And normally it makes more sense if you have a lot of features, input features. And then what SHAP will do, it will change the selection of input features and check against the predictions and then see how the prediction changes. And this gives an indication of which features have the biggest impact. And then you run again here, called run explainability. This executes the job. And I'll show you the result. In our case, it's not too exciting because we only pass review body and product category. And actually, the model only uses the review body as the relevant input feature. So you will see here that SHAP definitely identified the review body as having the most impact on the prediction. But imagine you have a use case and you're passing in maybe 10 input features, 100 input features, who knows. This will give you a really nice calculation of which ones contribute the most to the model predictions. And I do have here an animated GIF in the notebook that shows you just a sample when it's running with more input features here on a different use case. So you can see here nicely the visualization. All right. And the last one, I know we're running a little bit over. Sorry for that. The last notebook here, 11, is deploying the model now. So if you run this, what will happen is we're checking that the pipeline has finished. And we're using the trained model that we have. So I'm just checking here for this step registered model. And here I do have the ARN, the resource identifier. And I'm creating a model endpoint now. So you have two ways to deploy, generally speaking, models and serve predictions. You could either do it in real time. So this is useful if you need to integrate it into an application and you need to call that API and get your model predictions 24/7. And the second option to deploy a model is as batch. So for example, you have data sitting, for example, in an S3 bucket, and you need to run predictions on the data, but it could be done in a batch operation, right? You could done it on a job-by-job basis. And this is also possible with SageMaker. So what it happens, it spins up the endpoint, runs the predictions in bulk, and then saves the results into an S3 bucket again and terminates the endpoint. What we're showing here is how you can spin up the first option, so real-time endpoint, and you can call it with an API from any application that you require. So again, we're checking here for the pipeline model name. This is our trained model. And we're creating a model endpoint. So here we're calling the create model step. And here we're creating an endpoint configuration. So the endpoint configuration contains, again, the information about which instance type to use and how much traffic do you want to send it. So in this case, we're sending all traffic to this variant, basically. You could also deploy, A/B testing, for example, and say, I want to shift 50% of the traffic to this variant and 50% of the traffic to the other variant to do model A/B testing. In this case, we just deploy our pre-trained model here and send all of the traffic to this endpoint. All right, it takes a few minutes for the endpoint to get deployed. We put in again a deep link here, which takes you to the console. And you can also see this if you navigate here on the left under Inference and Endpoints. I think, yeah, here it is. My endpoint is deployed in service. This one takes roughly 7 minutes. Again, it spins up the underlying instance and then downloads your trained model. And then also gives you here the URL, which you can embed in your application. So you can call this API, this REST API, and receive predictions from the model. We're showing you in the notebook, actually, how this works. So we're creating also just here from the code, which is courtesy here of the SageMaker SDK, a TensorFlow predictor object, where we're just giving it the pipeline endpoint name, the session, the model name we're querying, and again, which format. So again, we're using JSON lines here as the accept type of the model. And then we can send sample data. So here I'm just creating a sample input feature. Let's say this is great as a review. And the second one, this is awful. And we can send those inputs then in the JSON format to this predictor object and see the results. And here we can see the first one comes back, this is great, comes back with a label of a 5. It's actually pretty good. And the second one, this is awful, comes back with a rating of a 1. So we see our text classifier is working. And this is the way how you can serve real-time predictions with the trained model. All right, so this was a quick walk through those individual steps. Again, we will keep the demo accounts up for another hour, so you have enough time to finish the execution of your notebooks and poke around. And you can always find the code in our GitHub repo. And if you liked the workshop today, we would appreciate if you would give us a GitHub star. We love those stars. And yeah, happy to hear your feedback. If you enjoy reading the book, we would also appreciate if you leave maybe a review. So we're big fans of 5-star reviews, as you probably know after this workshop. So if you feel like it and you like the content, feel free to leave us a review, maybe on Amazon.com, or give us a GitHub workshop star. All right, and with that, back to you, Chris, and maybe we can wrap up some final questions here.
Yeah, a couple questions on how to run this after today. So, Ancha, let's flip. Is it the QWK one? Quick start one. We flipped the README the day of, because we do different variants of this workshop. So we will flip back the README back to how it would be. It's kind of a weird way. We shouldn't do it that way, but that'll show you how to actually create Studio in your own accounts. If you already have Studio running, you just skip those steps. But really, it's just git clone and then start running these notebooks. As long as you know how to get into Studio or use the Studio Quick Start to get Studio installed, you can run it. Yeah, everything is public. Let me send you the GitHub repo here. On Slack, GitHub repo. Actually, let me just send you all the links. Don't forget our book. If you do read the book, we do ask that you write a review. We only have like 8 reviews, and 2 of those are from me and Ancha, I think. So yeah, but like once again, we've sold, we've exceeded the lifetime number of books sold within the first month. So we're seeing really good. We're seeing quite a lot of bulk orders, actually, is what we found out, where companies are buying the whole book for their whole data science team, 900 at a time, 1,000 at a time. Yeah, I know a lot of people, internal groups within Amazon, Amazon.com, have found it very useful. We put a lot of work into this and hope you found it as valuable as we do. And hopefully we see you soon. We are always changing the workshop. Again, as new features roll out, as new gaps get filled, or performance improvements or new instance types, we are always reevaluating, putting them into the workshop. So yeah, check out the book for the full 12 hours. Pretty much walks you through it. We developed the workshop and the book at the same time. That was on purpose because we, A, like we needed working samples to include in the book, and B, we, needed to get our hands dirty with all of the features that, potentially we don't use on a daily basis with customers, or just, small number of customers. So we cover multi-arm bandits. Yeah, what else? Ancha streaming. Ancha wrote the streaming chapter, one of the more popular chapters. Kafka, Kinesis, doing real-time machine learning updates. The multi-arm bandit stuff's really good in the deploy chapter. A/B tests. Yeah, what else? Traffic shifting.
Yes, and also, yeah, we added a chapter on security as well. So if you're
Security.
interested, and this is more maybe the people that work on maybe securing the cloud infrastructures, but we added a full chapter on how to run the security data science projects on AWS with a lot of good insight. Knowing it's not maybe the data scientist job, but if you have people in the team that take care of setting up the secure environments, that's definitely also worth passing on the book to them. Yeah, the deployment section is really cool. We also go a little bit more into detail in the pipelines. We had a couple of folks today here asking, I saw on the Kubeflow section. So we go into a lot of more details in pipelines in the book chapter discussing Kubeflow. We also have examples on Airflow. People sometimes ask using AWS step functions as an orchestrator. So if you want to look into those options as well, it's definitely also a good chapter to read.
Yeah, pipelines was actually, I think, one of the last chapters, right, that we built. It had to be because SageMaker Pipelines came out in December, just a few months ago. So we had to prepare for that. Yeah, Kubeflow, Airflow, step functions, TFX, for those of you familiar with TensorFlow's TFX project, we have an example there. And I saw someone asking about SM projects and the ML ops. So when you're ready for it, the next step beyond it's kind of a boring, yeah, anything automation seems really exciting until it's actually automated, and then it becomes boring, and which is the whole point. Like, you're not supposed to pay attention to it after that. It should just work. So I just pasted the notebook in there that is really the next step. So we sort of did an ad hoc pipeline. I mean, it's still a pipeline running on a cluster, but we built it up through the notebook. When you really are ready to automate, and of course, yeah, we cover this in the book, you would switch to that notebook there, which kind of walks you through how to set it up to run, based on a trigger as new data is coming into S3. Pipelines does integrate with a lot of other AWS services, of course, SNS and the Event Bridge, which, if you're familiar, used to be called CloudWatch Events, I think, has now been rebranded to the Event Bridge and has triggers for basically everything. So yeah, the streaming one's really good. Optimize hyperparameter tuning, 08, let me put that in here too. And distributed training. So we have, the different hyperparameter tuning and distributed training options. So thanks for joining us today. Sorry, we're about 15 minutes over. I tend to babble, and I'll stop myself now. So have a good weekend, everyone.
Thanks everyone for joining today.
Thank you.